Welcome, everyone. We're going to talk about my favorite routing protocol called BGP, or the Border Gateway Protocol. My name is Michael Gibbs. I'm the founder and CEO of Go Cloud Careers, and I've been working with BGP now since about 1996. So it's been a long, fun time of BGP for me. I am a Cisco certified internet expert. My number is 7417, and we're here today to talk about BGP for cloud architects. We'll talk about what is BGP. We'll talk about how does BGP work. Then we'll get involved in some thought experiments on traffic engineering with BGP. And then we're going to get real geeky. And my associate, Mark Milovanovic, is going to walk you through the situations on the routers. We're going to play with the routing table. The routers, you can see, how the routers are configured. You'll see how routes come in and out via BGP. If you want to see the BGP rib or the BGP fib or any of the cool, geeky BGP stuff, we can show it to you. We'll break some connections and show you how BGP fails in real time. We'll show you how to load share without getting out of order packets. It's got to be fun because I love BGP. And I know Mark does too. Before we begin, I want to tell you about 3 free things we have to assist you in your career. We have a document that goes along with this called BGP for Cloud Architects. My team will pop that in the chat box and download it. It's free. We had lots of fun putting this document together because, like I said, I love BGP. It's just exciting stuff for me. We have on next weekend, starting Friday and all through next weekend, we're going to be doing an AWS Advanced Networking. I'm going to be putting my propeller hat on to get a little geeky. Mark is going to put on his propeller hat and get a little geeky. Mo from our team, who's also a Cisco certified internet expert, is going to put on his propeller hat and get a little geeky with you. And Benjamin, who's an incredible network architect, is also going to get involved. So we're going to have lots of fun. So download these free resources, and we'll begin in about 2 minutes. Mark, why don't you say hello to everyone?
Welcome, everyone. I'm happy you all could make it. It's always a pleasure and honor to see that you guys could take the time out of your day to join us. I hope you're going to enjoy the theoretical lessons about what BGP is, why do we use it, and then as well as when we get onto the command line, we're not so much going to focus on the actual configuration of BGP. That's not what this particular workshop is for, but we want to see the before and the after when we actually apply policy. And that's where BGP strength really comes out, is the policy application compared to just the other things you'll hear us talk about, the scalability and so forth. But in any case, I'm really excited, Mike, and I think this is going to be a super fun workshop for everybody.
Yeah, and I'm excited because, we've got somebody that's going to show it physically, going to show what's on the router. Can you guys give me a hashtag? I want to know that you're awake, alert, and oriented because we're going to get pretty geeky today. So can you give me a hashtag BGP for Cloud Architects? Because that's the title of today's session, BGP for Cloud Architects. If there's 60 of you guys here or 70 right now, hopefully we've got 70 hashtags, and I know that you're actually here and awake. Because I like to know that the audience is awake before we start piling on all the geeky stuff. And we're going to get a little geeky today. Unfortunately, there's no way to get around BGP without being a little geeky. So we'll have some fun with it. Sometimes you just got to get geeky. So I'll wait and see some more of these come in. I'm seeing some of these BGP for Cloud Architects pop up, which makes me happy. This is critical cloud networking information. These are critical networking fundamentals for cloud architects. So I see you're here. I see you're awake. I see you're alert. I see you're oriented. Valerie out there, you coming up with the acronyms. In class we got that acronym-based swear jar. We'll have some fun with that, Valerie. Valerie, you know me and you know me real well. It's good to see you here, as well as others that are here. Okay, so we'll at least begin an introduction to BGP. And we're going to talk about what is BGP, why we use BGP, and how BGP works. And let's face it, we're going to get a little technical. So BGP is really a routing protocol, and it's actually an application at the same thing. The application of BGP really functions as a routing protocol, and it will determine how we get information about routes that exist in our network. So before we get into any of this, if you're not network architects already, I want to make it clear to you, if you don't have a route to something in a network, you can't reach it. So kind of like going to your friend's house. If there's no road to get there, you can't get there. But what if you were trying to, you're live in Florida like me, and you have a friend that lives in Tennessee, and you want to visit your friend in Tennessee, but you don't know what roads to take, where Tennessee is, or how to get to Tennessee in the first place? Can you get there? The answer is no, because if you don't know how to get there, and you're trying to leave Florida and go visit Tennessee, you might be circling the United States. You might make it to New York or New Jersey or San Jose, California, or Houston, Texas, and miss Tennessee completely. So in the networking world, if you don't have a route to it, you can't reach it. So when it comes into routing, we really have two options. We've got the manual intervention option, and we've got the automatic option. Here's the manual intervention. We tell every router how to reach every subnet in the entire network. They're called static routes. So you've got a network that has 5,000 routers, and on those 5,000 routers, you have 15,000 routes. You could go to every router and put an IP static routing statement, IP route this subnet to this subnet to this interface. You could do it. Now, what happens when one link breaks? You're stuck because the routes are static. And it kind of reminds me of the old days when I wanted to go visit my friend. What I would do is I would take a map book, and I would say, let's say I wanted to go from Florida to New Jersey. I'd say take I-95 north for this many miles, make a right on this exit, go onto this road, go onto this road, go onto this road, go onto this road, and I'd list myself my 50 steps. And it was great until the road was blocked, and I didn't know how to get there because I had no idea. We didn't have GPSs in those days. Well, that's the same thing. If you've got static routes, you get lost once anything changes. So static routes don't really heal. By comparison, dynamic routing protocols are the routers themselves asking each other, how do I get from point A to point B? And the way they do this is they basically build a database that has a list of every place they could potentially go to for the most part. All these routing protocols are a little different. And then they run through that database, they run through their calculations and build a path. So dynamic routing is just like the GPS in your car. If I'm going to go to Chris's house over in there in that St. Petersburg area, it's going to give me a path. And if one path is blocked, it'll reroute me around another path. And that's why we use routing protocols and networking, to find where the systems are and how to get there, and to make our networks heal. One link goes down, it's okay, the routers recalculate our paths. And they do this by building something called the routing table. So now we've described basic interlevel routing. So now we've got to choose a type of routing protocol. And we realistically have two kinds of routing protocols, and Mark will show you both today. We've got interior gateway protocols that we use inside of our organizations to calculate our own routes. And they're tuned for speed. Cut a cable, 5 seconds later, you know about it, and the routers can recalculate, or 10 seconds or something like that. They're interior gateway protocols, but they don't scale well because they're designed for small areas. They're fast, and anytime you get fast, you lose scalability. And then there's what's called exterior gateway protocols, which are what you use to connect to external entities. When I connect to the internet, is the internet internal to you? No, use BGP. When I connect to AWS, is AWS internal to you? No, use BGP. When I connect to Azure and AWS, are they both external to you? Yes, you must use BGP. So that's really what we're talking about here. So BGP is a little bit different than other routing protocols because it's an exterior gateway protocol. Most routers discover each other. They basically send what's called an IP multicast. I'm here, everybody. Who else is here? That's normal routers. They route via multicast. RIP did it. EIGRP uses it. OSPF, all those interior gateway protocols. They actually tell each other they exist. But not BGP. BGP, you must manually tell the neighbors that are there, and that's for security. If I want to connect with Mark Milovanovic on the other end of this call, I take my router to his router, and we manually tell each other to connect. So BGP is manual for security purposes, and BGP uses unicast packets. And BGP is reliable, meaning if I tell Mark about a route, I need to make sure he got it. And if he tells me about a route, he needs to know that I got it. And the only type of networking communication we can use for that is TCP, because it's reliable transport. So routers connect to each other using the BGP protocol with TCP. And it happens to use port 179. Why am I telling you TCP port 179? Yes, it'll be on any networking exam you'll ever take or cloud exam you could take. The BGP uses TCP port 179, but that's not the reason why. Between router A and router B, you may have a firewall. And if you don't know how to open TCP port 179, BGP will not work. So you have to remember that BGP uses TCP port 179. We use BGP because of its scalability and tunability. And what do I mean by scalability? If you were to connect to the internet right now via BGP, connecting to your internet service provider, you'd get about 900,000 routes. It's a lot of routes. To put it into context, when you connect to your cloud provider, you have 100 routes. But when you connect to the internet, you're going to get 900,000 plus routes. So that's the size of the internet routing table. And you may be getting these 9,000 routes from 15 different internet service providers. So you can think about it, let's say 900,000 is a million. That's 15 million routes sitting on the routing table with all their attributes. That's why we use BGP, because it's scalable. The second reason we're going to use BGP is because it's very tunable. BGP has these things, we call them nerd knobs. Nerd knob 1, nerd knob 2, nerd knob 3. We're going to get into this. And these nerd knobs in BGP enable us to traffic engineer, meaning I've got 2 links. I can load share across both links. And we'll talk about why we need to do that under certain circumstances. So BGP is really cool. It scales well. It's tunable. And we can customize it to pretty much do anything we want. And that's completely unlike every other routing protocol. So BGP has to form a neighbor relationship. If Mark, who's sitting on the other side of this call, and you're going to get to see from Mark soon, he's going to get lots of fun with you and get you real good and geeky. But if Mark and I want to talk to each other, we have to form a session between us. And that session relationship between BGP speakers, or me and Mark, is called a neighbor relationship. And I mentioned earlier that we have to manually configure these, and you can see how we do these things if you desire this afternoon. And I have to go through a series of messages. And in order to understand BGP, we're going to have to understand the message type. I'm sorry, we're going to get geeky here. And then you're also going to have to understand the finite state machine, which we'll get to in a little bit. After that, we'll talk about how to traffic engineer. And again, then we're going to get into the fun stuff. Mark is going to bring us to the fun. So BGP is going to have 4 messages that we need to talk about. And it's going to be an open message, and we'll talk about what we use that for, a keep alive message. And for those of you that are familiar with health checks on load balancers or health checks on DNS, it'll come familiar to you. We're going to talk about an update message and a notification. So what really happens? So Mark and I were 2 routers on the other side, and we're also 2 CCIAs, and we're also 2 network architects that like getting geeky on networking. But anyway, so Mark and I decided to form a neighbor relationship. First thing that happens is we start a TCP session. You know, the SYN, the SYN-ACK, and then the ACK, and then all of a sudden we're now allowed to talk to each other. And as soon as the 2 routers establish that TCP session, the router sends an open message to each other. And why are we doing this? Well, if Mark and I are going to talk to each other, we've got to send an initial message that identifies ourselves. Mike's router, Mark's router. And it's going to specify any kind of BGP parameters we're using, because we need to maybe be able to negotiate certain things like version numbers, etc. So that open message will have our BGP version number. It will have our autonomous system numbers, which is how we identify ourselves in the BGP world. It will have something called a hold time. And what's a hold time? A hold time is the maximum number of seconds that can elapse before a BGP router will receive a keep alive or a health check or an update message. And if we don't receive these routers within the hold time, we'll drop the TCP connection because we'll assume it's not there anymore. So BGP version number, BGP identifier, which is typically the loopback address on the router. For those of you who know what I mean by a loopback address, if you don't, it doesn't matter here. It will include the autonomous system number identifier and the hold timers in that open message. Now, BGP router 1, BGP router 2, they've got their TCP message. Now they send the open message to each other. Now, periodically, the 2 routers need to know if they still exist. So, you know, the way a load balancer would say to a server, are you there? And the server would say, yes, I'm here. And the load balancer would say to the other, are you there? And the server would say, yes, I'm here. And that way the load balancer knows if the server is healthy or not to send traffic to. It's the same thing we're doing here. Router 1, router 2, BGP neighbors, they send keep alives to each other to keep the session up. Just a health check. Don't receive the health check in a period of time, get rid of it. So now you know what the open message is and the keep alive message. Pretty simple stuff. Here's the update message. Mark and I are connected to each other. I learned about a new route. Mark is my BGP neighbor. And I got to tell you, hey, Mark, guess what I found out? I got a new route. But if you think about it, let's say there's this new action film that Schwarzenegger and Sylvester Stallone come out in. As soon as I hear about it, the first thing I'm going to do is call my brother. Hey, we got an action film to see. Isn't that the same thing as an update message? We all like different movies. I don't get to watch a lot of those movies. I watch what my wife likes. But, you know, every once in a while, I get to go out with my brother when I'm in Philadelphia, and we get to watch action movies. So what's really contained in these BGP update messages? Network layer reachability information. I didn't make this. Basically, it's just the subnets or routes that you're getting. So these update messages are saying, I've got these new routes. And when we send the update, we have to talk about the attributes that come with the route. Now, we'll talk about those attributes in a little bit. Those attributes, which are tunable, which are our nerd knobs that enable us to take things away. Now, the other thing that's part of these update messages are routes that we no longer have. And why would we do this? So Mark and I are BGP speakers. We opened our TCP, we established our TCP connection. We opened the session between us with our open messages. We're sending our keep alive, so we're both happy and healthy. And then I lose a route that I was going to use to reach a website that sells tuna. My cat loves tuna, so let's say there's a besttuna.com website. There probably is. So but let's just assume we made that up for right now, or it's a real site, whatever. If besttuna.com doesn't exist anymore, I shouldn't have it in my routing table, and I should send it to my neighbors that besttuna.com doesn't exist anymore. And that way, we don't send traffic for besttuna.com. So now you know what's in the update. Now, the last message we need to talk about is a notification message. Well, how many of you like getting letters in the mail that are notifications about something? Maybe you live in a homeowners association and your grass is 1 inch too long and you're getting fined. Maybe your brother, your sister, your cousin put a recyclable in your regular trash and you got notified and you got fined. Well, that's really what we're talking about, a BGP notification message. So you've got your 2 BGP speakers and an error is detected and a notification message comes out. So if you had 2 routers that tried to form a BGP relationship and one was BGP4 and one's BGP v3, they don't want to talk to each other, then you get a notification. So opens up the connection. Update sends information about routes. Keep alive says I'm here. A notification, something bad happened. So now we're going to get into the finite state machine. BGP uses a finite state machine. Chris, if you can share this slide very quickly. I'll show you what I mean by a finite state machine, and then we're going to go through these messages. Here's the thing, and there's a mathematical term for finite state machines, but in networking, what it really means is we've got a system that's supposed to work in a certain way, a certain function, and a certain manner. And if one thing occurs, we're going to transition from one state to another. And if one thing is expected to occur and it doesn't, then we may transition to a different state. So that's really what we're talking about in terms of finite state machines. Lots of protocols have finite state machines. OSPF has a finite state machine. BGP has a finite state machine. And it's just going to be the way that it works in a given manner that's going to be very predictable. If this, then this. If this doesn't happen, then this happens. If this happens and then this happens, we want to go here. So Chris, you can take that slide down. And then we'll talk about that BGP neighbor relationship, and we'll go through this finite machine. So if I start my BGP neighbor relationship, I'm going to be in one of three states: idle, connect, or active. So let's talk about what I mean by and that's going to take us to the open send, open confirm message. We'll get there in a second. So where do we begin? If I've got 2 routers here and they start out, they're idle. They're not talking to anyone. So the second you start BGP, and Mark's going to take you to the routers and he's going to maybe do some debugs and you'll be able to see this and it's going to be fun, fun, fun. But at least if you understand what you're seeing, it'll make sense. Otherwise, it's just going to be stuff that floats on the screen and kind of be like all those error messages that you'd see sometimes. You got to know what they mean. So the BGP routers are going to start out as idle. Idle is when the routers are waiting for a TCP connection to be established. If there was an error, like I configured this to reach Mark, but I got Mark's IP address wrong, we're not going to connect, and these BGP routers will never transition out of idle. So the two routers connect to each other, and that open message is sent. We've got a TCP connection. So realistically speaking, now we're now in the connect state. TCP connection went up. Open message was sent is good. TCP connect. Now, should something have gone wrong, we're going to transition into a different state called active. And I want to keep that in the back of your mind. Connect. The way it's supposed to happen. Idle, connect. This is good. But if we've got a problem, we're going to transition to the active state. Generally speaking, I want you to think of the active state as something went wrong. So when we go through this process of idle and connect, if something doesn't occur, we're now going to transition to active. And active is where BGP will try to reinitiate the TCP connection with its neighbor. If the TCP connection is going to be good, it's going to transition into open sent. If the BGP connection is bad, it will go back to idle. So active is this sort of placeholder where something isn't right. It should go straight from open a connection, go to open, and then transition straight to open sent. But if it doesn't, you're going to go to active. And if it's when inactive, it opens the connection on both sides, you're going to transition to open sent. And if it doesn't, this connection does transition, you're going to go back to where we all began, which was idle. So now we're in BGP. The TCP connection went up, the open message was sent, and we've reached open sent. Now, things are starting to get better. At this point, if things are good, and we transition from open to open sent and keep alive, when both routers are going to send each other a message. Hey, I'm here. I see you. I hear you. We're together. If we've got a problem, where are we going to transition? Back to idle. So I want to make it clear we're supposed to be going forward. But if things fall apart, we go backward. And all that active state is this transition, this in-between state where we give it other chances. Now, the next thing, we've got our routers. They went to open. They went to open sent. And that worked perfectly. The keep alive was sent. And now they're in this open confirm state. And you guys have all this information written down for you in that free BGP document we wrote for you. And if you don't have it, please download it. It's completely free in case you just came. My team will pop that in the description in the chat box for you. So BGP now sends, we're now in open confirm. Now at this point, if it breaks, we go back to idle. But assuming everything worked, our TCP messages, our keep alive messages are going good, now we're going to transition into established. Now this is where the magic happens. I've got a connection to my router. It's connected to Mark's BGP router on the other side. We're established. Now at this point, I'm going to be sending this information to Mark. Mark's going to be sending his information back to me. We're going to have all this stuff in our BGP table. We're going to then figure out which routes we pop in our routing table, and then we know how to go everywhere. So there you go. TCP connection is set. We go to open. We go to open connect. Keep alive sent. We go to open confirm in that area. Then we go to established, and then we start exchanging routes. So now we get to BGP attributes, and then we're going to get to play with this and see it in real life. BGP attributes, and we'll also take questions, obviously, but BGP attributes are information that's contained in the routes about the route itself. So imagine if I had two cars. I might be able on one car to write on the top of the car, big engine. And I might be able to put right on the other top of the car to categorize it, so to speak, that says sport suspension or something different. And I might know to utilize each car. I might then want to, determine which load I'm going to place on which vehicle, right? Well, it's the same thing in networking. We want to determine sometimes where our traffic goes. We have to. And the only way we can determine which route might be better are going to be based upon the attributes in the route itself. So just extra information to help you make a decision. And we're going to have fun with these attributes. So let's talk about some of these attributes. One of them is called the origin. What does that really mean? It's how we learned it. So if a route that's in our BGP table we learned through our local interior gateway protocol, say OSPF, because it's inside of our domain, that's going to be preferred. Now, if we learn it through a BGP from an external organization, guess what? Then we call it an EGP. We learned it externally. And what if we don't know how we learned it? How believable is that route to you? One, I know where I got it. I got it from my internal network. One, I know where I got it. I got it from my external network. And now I've got it, and I don't even know how I got it. So internal network's most believable. External network's second most believable. And we don't know how we got it as the third most believable. So we will be able to use this origin attribute, this nerd knob, to influence our traffic when we want to. So keep that in the back of your mind. Your origin is where we learned it. Now let's talk about the next attribute, the AS path. What's the AS path? So every organization, and we'll show you, will have its own autonomous system number. So if I'm autonomous system 1, and then I give it to autonomous system 2, and autonomous system 2 gives it to autonomous system 3, then when we get to autonomous system 3, it's going to see that it learned the route via autonomous system 1, 2, and 3. It's the train of where we caught it. Kind of like in my company. An idea comes to me. I ask Chris if it can be done. Chris says, yes, it can be done. And then he assigns the staff to do it. No different than what we're really talking about. And, the closer it is to the source, the more accurate the information is. And so now you understand what is AS path. It's the path that we took to learn it. So guess what? If we learned it via 2 paths over here, and we learned the route via 3 paths over here, wouldn't you think, all things being equal, the shorter path is better? So that's really all we're talking about here, is the autonomous system path. The shorter the path, the better. So we talked about one attribute, which was the origin. Now another attribute is the AS path. Now the next attribute is called next hop. Where do we send the packet to the next hop to reach its next destination? And guess what? Maybe Mark will debug this if we don't have the next hop available, if he feels like it, or if you guys have extra time and you want him to, because we can get pretty geeky, Mark and I. If the next hop is not available, it won't be in the routing table. Whoa, and I have lots of people, I've seen them configure BGP. The next hop isn't reachable. The route doesn't show up in the routing table, and nobody can reach it, and they can't figure out why. I'd say a third of the networks that I've troubleshooted in my youth had that issue when they tried to set these things up. So the next hop is super important. So origin's how you learned it, internally, externally, or you don't know. AS path is which systems did you go through, which ISPs did you go through along the way, so to speak. Shorter path better than longer path. And next hop, if I can't reach it, don't send the route there. Very, very simple stuff. Now, Cisco came up with this proprietary attribute called the wait. And they decided to give you the opportunity to the wait, and they said, hey, the bigger the wait, the better preferred your traffic is. Now, it was a Cisco proprietary attribute. It's now used in cloud computing. You can use it with AWS, for example, and others. Wait is just a little nerd knob, a little tune for you to tune that says, make it better. The bigger the wait, the more preferred. So, origin, how we learned it. Internally is more reliable than externally, which is more reliable than I don't know. Hope that makes sense. So that was one of the attributes we went through. The AS path is how we learned the route. Less paths along the way, more logical, to be the faster. Next hop is if I can't reach it, the next place to send it to, why send it anyway? Because if you can't reach the next hop, it can't get to the ultimate destination. And this one's the weight. The bigger the weight, the more preferred. So now we know what these attributes are. And now BGP will select a path based upon these attributes. So here's the decision tree. Here's the algorithm. On Cisco routers and AWS, prefer the path with the largest weight above all else, which means if weight means the most to influence your outbound traffic, if you raise the weight, you can take this link versus this link. Now, what if the weights are equal? Now we've got another attribute called local preference, where you can tell it which one you want it to take. The higher the local preference, the more preferred the route. So prefer the path with the highest weight, prefer the path with the highest local preference. Next, if the local preference values are the same, prefer the one that was originated on the local router. This is the BGP path selection process. Well, if you learn it from yourself versus you learn it from somebody else, it's probably more reliable. Then we're going to look into the shortest AS path. So less paths to get to the route. But remember, we started with highest weight, then we went to local preference, then we went to AS path. So if the AS paths are the same, now we're going to use that origin code. Remember the origin attribute where I told you where learned internally is better than learned externally, which is better than learned via I don't know. And then if all that's the same, then we're going to be looking at the multi-exit discriminator, which is a metric to leave the autonomous system. Lower med is preferred. Now, once we get past all this stuff, we still need an election process to choose the best route. And we start getting into the wackadoodleness. So if the routes are still equal, prefer the shortest path to the BGP next hop. Okay, that's fine. And if it's still equal, now we're going to look at the path advertised from the router with the neighbor's lowest IP address. So this is where we start getting into old kinds of things along the way. So let me go over it one more time to really think about it, and then we will start actually having fun with it. Choose the route with the highest weight. If the weights are the same, choose the routes with the highest local preference. If that's the same, choose the routes that this router locally originated. And after that, take the shortest AS path. After that, choose the best origin code where IGP is greater than EGP, which is greater than unknown. And after that, choose the path with the lowest weight. Then we take EGP routes over IBGP routes. Then we look at the closest next hop, basically closest neighbor. Then we start saying, hey, what's the oldest route we have in the table? And then we'll choose a path through the router with the lowest router ID. Again, like I said, now we're getting random and silly. And then choose a path with the router with the lowest IP address. So Mark has a mnemonic for you guys, and he called it he say how does it is WE for weight, love is in local preference, oranges is in locally originated, as is in AS path, oranges is an origin code, then mean is for the med, pure for paths, and refreshment. So we love oranges as oranges mean pure refreshment. That is a totally way to look into that. That's Mark's genius idea. I just memorized the chart in my head. Any way you want to learn it is good. So actually, I'll actually pop his up on the screen. This is the way this is the way Mark from our team likes to remember it. He used the mnemonic, we love oranges as oranges mean pure refreshment. All right, so Chris, you can take those slides now. Now we're going to get into the fun stuff, but if anybody has any questions, where we're going to actually talk about how to do some traffic engineering, and then Mark's going to do the traffic engineering, which is even more fun. But I want to make sure that if you've got a question, we can answer it for you.
All right, Kwaku asks, what is a good way to remember the difference between the way TCP connects and the way DHCP connects? Well, Kwaku, first of all, DHCP does not connect,
Right.
period. So DHCP only gets invoked when it receives a request, basically a discover message for an IP address allocation. DHCP is initiated by the client towards the server. And once we get into the actual demonstration, I'll show you that, because BGP will run on top of IP, on top of TCP, and we'll be allocating an IP address and, of course, a port number, which we call, lovingly in networking a socket, but just remember it binds them to, so it understands where the information eventually has to go to. So, and I believe there's a mnemonic, well, not mnemonic, there's an abbreviation, I think called DORA for the DHCP process, the way you can remember it, the way the messages go back and forwards. For TCP, I don't recall that there's anything in particular. It's just a SYN, an ACK SYN, acknowledgement to the SYN message, and then a final SYN message, which we'll see again as we go through different states, that basically says, I agree to have a conversation with you.
Yes, and obviously we teach these things in our course, but this book honestly will help with a lot of these TCP, UDP, ICMP connections. This book has been around for 30 years. Every Cisco certified internet expert has one of these. And this book covers nothing other than TCP IP. So it'll cover some things like DNS, it will cover DHCP, it will cover the way TCP sets up a connection, it'll cover the TCP sliding window. It doesn't cover any of the networking stuff like routing protocols and things, but just TCP IP. Excellent information into the Stevens book. Highly recommend it. While we're here, if you guys are having a good time, if you can hit the like, if you're not a subscriber, subscribe. And please, because we're going to get geeky, download the completely free BGP document we wrote for you. My team will pop it into the chat box. And in addition to that, we have the free AWS Advanced Networking Bootcamp that's going to be taught by 3 CCIEs and a CCNP. And obviously our team has passed that exam. It's a pretty entry-level exam, and we want to help get you through that AWS Advanced Networking exam.
So it says, hi, Mark, Mike and Mark. What are some of the best ways to secure a BGP connection to prevent route hijacking? All right. So those are two separate things, just so you understand. The connection is generally between what we call BGP speaking peers. Okay, so that's where we now look into how do we prevent a man in the middle attack, in a sense, or denial or distributed denial of service attack. So what we have to do is we have to control who we connect to, because any external entity by default we consider it untrusted. That is the difference between an interior gateway routing protocol and BGP. And what we have to do is we have to secure the point-to-point session that we create between the two speakers while using TCP. So that's also important to remember. And for that, there's different mechanisms that we're going to do, that we're going to use. I'm going to show you when we get into the demonstration. I'm using a particular feature called TTL security, where I'm actually hard coding that the peer can only be a directed connected peer, meaning there can be no additional hops in between, unlike what we'll see in the iBGP type of sessions, where you can be more than a single hop away from me. So that is one way of securing the session. And when it comes to actual route hijacking, what you have to do is you have to basically prove the origin of a route. And that's done through a combination of a additional community tag that is included in the update message. That is basically the route of, I believe it's called the route origin authentication. I think that's what I believe it's called. And that gets coupled together with caching servers, where you have to actually look into it if what was advertised. And this is, by the way, this is all most of these are maintained by the regional internet registries. And what they do is you'll have a list, a database where you can go to. You'll look at what is my prefix, including my prefix length, basically my network address and my subnet mask, and what is the autonomous system that it's coming from. And then that gets checked. So that kind of works in conjunction to each other. And then what you have also, you have digital certifications that get attached to this, that also through a public and private key, it proves who you are. So in between the different caching servers and you. And you have to actually download that database to your router so it can do the actual line-by-line check. So it's a little bit more involved. They're pushing for that to become good practice. So we'll see how that goes about, but that's what you would technically do. But believe it or not, that is so far out of the purview, not just of this workshop, but even the CCIE. It's not even funny. This is predominantly done if you want to do it at your location, if you have a large address space and you want to verify what you let in. Of course, service providers, they want to use it because many times we have these different tiers of service providers, a tier 1, a tier 2, and a tier 3. They all interconnect to one another to allow basically the traffic from one autonomous system to another one. So we have this transit kind of problem. And then there you have to verify what the routes are. But it is quite involved, to say the least.
And one other thing is, we also have to filter the routes in that we expect to be receiving. It's just standard BGP practice.
Yeah.
So if Mark is an ISP and I own the 10.1.0.0/16, and Mark's connecting to me, I should only be able to give him the 10.1.0.0/16. If I send him the 10.0.0.0/8, he should block that. Because, well, actually that must an aggregate, but if I send him the 10.2.0.0/16, he shouldn't be getting those routes from me because I don't owe him, and he should block that. And if we don't allow routes in that we know not to be from the correct source, we can solve a lot of these things too. And these are standard BGP practices that unfortunately not everybody follows.
And from Cloud Station, he asks, how does BGP work between 3 autonomous systems belonging to the same organization? You want to tackle that one?
Yeah, so let's talk about why we might do this. In a normal world, we have one autonomous system number for the whole company because it's all under our domain. Let's say we're a cloud provider and we want to come up with some separation between our European parts of the cloud, our USA parts of the cloud, our Middle Eastern parts of the cloud, and our Asia Pacific Rim parts of the cloud. We could divide them into their own different autonomous systems. And by doing so, we could limit, not eliminate, we could limit the blast radius. Something crazy happens in Asia Pacific, BGP could potentially protect those other autonomous systems. So we would do that. And how would we do that? We'd run each autonomous system independently. They would run independently their own interior gateway routing protocol, typically OSPF or IS-IS, because we're going to need the level of information that's contained in a link state routing protocol, especially if we're going to have to do any MPLS traffic engineering, which we probably will internally to these things. And then we're going to run BGP from every place that we need it, like autonomous system 1, 2, and 3 will all be fully meshed with eBGP. And internally, they'll carry their routes across via their own autonomous system via iBGP. That might be a fun workshop because we could do that and set that up and build it and design it, and we can show the strengths and weaknesses of each approach. And maybe we do an advanced BGP day. If you want to do it, if you want an advanced BGP day, Mark and I can do that. Let us know.
Follow-up question from Joseph. He asked, did I understand that IGP is trustworthier basically than EGP? I'm not sure if you were referring to OSPF and eBGP in terms of trustworthiness. Please elaborate.
So what I was referring in BGP, when we look at the origin code, they've determined that the interior gateway protocol is greater than the interior gateway protocol, which is greater than I don't know how I received it. But Joseph Dennis, let's think about this for a second. The interior gateway protocol is under your control, meaning you have 100% control over it. If you have 100% control, you can have relatively good trust that the information you receive is accurate. What you learn via the exterior gateway protocol is routes and information from somebody else. It's outside of your control. If your wife or husband tells you something, it's probably pretty believable to it. But if a stranger you've never met before gives you that information, it's probably less believable than your spouse. So that's really what we're talking about, where the interior gateway protocol is typically more trustworthy than the exterior gateway protocol, which would be better than I don't know where I got it from. Hope that makes sense.
Yeah, and I was just asking Dennis Joseph a follow-up question. See if he can clarify if he was specifically talking about the origin attribute, or if he was referring to the statement that I made that eBGP connections are by default considered untrusted compared to if we're running an interior gateway routing protocol such as OSPF. So do we have any other questions? And then we can always follow up. Okay, so from Singh, welcome to the workshop, Singh. He says, hey, can I ask you guys to explain why iBGP needs OSPF to work? And do we configure iBGP on every router inside of an autonomous system? Well, let me answer the first part, Mike, if you don't mind.
Okay. Yeah.
I'm going to demonstrate to you why we need that. There's a very specific reason why we need it, especially when it comes to when we're trying to inject the routes from an external source, such as BGP, into our internal network if we're running such things such as a OSPF IGP or something like that. The same will also apply, believe it or not, if we're running IGP inside of our network as well, because of certain rules that are in place that are going to differ on how the route is injected and what the next hop address is. But we'll demonstrate that problem when we get there. And when it comes to, do we configure iBGP on every router inside? Well, that depends. What are you trying to accomplish? If we're talking about you're just looking for a scalable way of injecting external routes into your internal domain, you might just run IGP on the edges of your network and just have them through, your internal network have BGP pairings up between the edge devices. You might do something like that. That's actually a scalable way of injecting external routes into your internal domain without overloading your IGP. That is one of the use cases I'll give.
And and we'll get involved in it. So why are we doing this, Preb? So I got 800,000 routes that comes into an internet service provider on one side of us, and now I've got another 800,000 routes on another internet service provider. If I want to carry traffic through our organization and the routes through our organization and provide transit services, I have to run iBGP across my network. If I don't want to provide transit and I just want to provide routing information, I may not need to, my goal is something very different. And if I have to provide transit across my network, I'm going to have to fully mesh my iBGP peers, or I'm going to have to create route reflectors to break the rules of the full mesh iBGP, which is kind of like Cloud Hub and Transit Gateway, everybody in cloud computing. Fully mesh your VPCs or break the rules by using this service to allow you to break the rules. So Cloud Hub, Transit Gateway, or just a BGP route reflector. Or I divide my BGP domain into multiple smaller subdomains, private, and create what's called a confederation, where I take a whole bunch of little mini BGP domains and put them together into a big BGP domain. So, saying there's a reason I spend 10,000 hours consulting in BGP, because we can get pretty geeky pretty fast. But as a rule, most organizations will not be configuring iBGP on their internal networks.
Yeah, what you want to keep in mind is, again, think about the different layers that we have or the way that systems operate. So we mentioned that BGP binds an IP address through a port, which becomes a socket. So it runs on the TCP, which is the transport layer. It then has to send that information down to the network layer because there has to be an IP lookup done on figuring out how to route the address. If that address is not in your routing table, again, we're not discussing on how it got there, just if it's not in that routing table, that's where you will have issues, because it's going to mark the path as inaccessible, meaning I cannot get to that next hop. Again, BGP is a bit more unique than an IGP. BGP only tells you about what we coined the phrase network layer reachability information. It's a fancy, basically, wording for a prefix and a prefix length, which becomes a route. The reason we call it network layer reachability information, though, is because BGP can do a lot more than simply IPv4. So it's like an umbrella term. But again, it just tells you about the route. It does not tell you how to get there. You'll have to figure that out. And that's usually done through an IGP. A good question. So Kukao, I hope I'm pronouncing it correctly, asks, hey guys, I've been asked during an AWS interview to explain what happens with packets sent on the wire, OSPF versus BGP, and how it works in detail. I'm assuming you meant hop by hop and so forth, to reach the destination. Any tips?
Yeah, so, and I mean, you have to learn these protocols if you're going to work in any kind of networking. And that means you're going to have to read, for real, the RFCs, the request for comments, which are written by the Internet Engineering Task Force. You probably need to read the Routing TCP/IP Volumes 1 and 2 book by Jeff Doyle. You're also at minimum going to need to read the Internet Routing Architectures book from Bassam Halabi to really know. And after that, quite frankly, you're probably going to need some training as well. Now, if you wanted to be a cloud architect and you were training with us, we'd cover these things because it's critical for architecture to understand how these things work. But if you were to try and learn them on your own, at minimum, I would say read the RFCs for BGP, read the RFCs for OSPF, read the routing TCP/IP volumes 1 and 2 from Jeff Doyle, and also read Internet Routing Architecture from Bassam Halabi. Great book he wrote.
And definitely, if they're asking you about anything on the wire related, you're going to have to get your hands dirty, unfortunately. So again, this is not so much of an architect type of practice, but during an interview, if that's what they expect from you, you'll have to do basically what we're going to demonstrate today, be able to set up a topology, do a debug, do a packet capture, and get a feel for what is the difference between how a interior gateway routing protocol, and that's also going to vary depending on what you're using, from ISIS to OSPF to EIGRP, and God forbid you're using RIP these days, is still all going to be a little bit different. So sorry, you got to get your hands dirty.
All right, let's get back to some content here. So now we'll do the thought experiments, and then we're going to get geeky, and Mark's going to actually do it. So Chris, if you put up, so actually let me walk you through it. We're going to have some fun with this, and then I'll actually show the answer. Let me draw them out real time. I like the real time whiteboarding session concept over here. Bear with me while I get this set up. If I share my screen, is this going to show up the right color? And then if it is, okay, it will. Okay, Chris, you want to share my desktop or my slides? Okay, so let's say you have an environment like this, where you've got your data center, or you've got your campus. It really doesn't matter. Bear with me, I'm going to get a little closer to my computer for this one. And you're connecting to your cloud provider. Let's say your cloud provider is over here. Let's say it's AWS. And let's say you've got 2 links to AWS. It's a pretty common scenario over here. You're going to have 2 links. Now, if we want a high availability system, everyone, do we buy our 2 links from the same phone company to buy our private lines? Private lines like a wire, are we going to buy them from the same phone company? Buy 2 links from Verizon? I hope you say no, because if we buy 2 links from Verizon, when Verizon has an outage, we lose both links. So this is not a good situation. In networking, you would never use one wide area networking provider because it's not good for availability. And that's the same reason you probably don't want to use a single cloud provider. But let's say we've got these 2 routes, and the top route, the top link is on, what do you call it? This link is on AT&T. And then we'll have another link, and we'll put that link on Verizon. And of course, we'll make sure that the cables underneath the buildings are on discrete fiber paths, so to speak. Now you can see we've got 2 links to the cloud. And we'll put the bottom one on Verizon. I think their stock symbol is VZ. So you can see we've got the top links on to the bottom. Now, in a normal world, we've now got 2 links. But we have a problem here. It's quite possible that our traffic can go out the AT&T link and then come back on the Verizon link. Now, why might that be a problem? Well, what if the Verizon link is 3 milliseconds and the AT&T link is 2 milliseconds? Then in this particular situation, we send our links, our traffic down one link, and half of it comes back the other link. And we've got half traffic coming back on AT&T and the other half of the traffic coming back on Verizon. And it's at random. The problem becomes as we get out of order packets. And our applications don't like out of order packets. Imagine watching TV and you get the first 3 packets, the next 50, and then you get the 4th packet. I mean, this isn't going to work. So whenever we're dealing with multiple lines to a provider, we have to engineer our traffic. And one way that we can do it is very simple. We actually just, what we do is we play with our subnetting information. So let me give you this particular situation. In this environment, if I had a 172.16.0.0/16, and I also had 172.17.0.0/16, I have two subnets, right, everyone? Two of them. These two aggregate subnets, these two CIDR ranges. What I could do is the option one is I take this, the 172.16, and stick it on the top link. There we go. Now all traffic for 172.16.0.0/16 will be on the top link. And now what I can do is take 172.17 and stick it on the bottom link. Now all my traffic for the 172.16 goes in the top link. All my traffic for the 172.17 goes in the bottom link, and everything is great, right? It's working. It's perfect. No out of order packets. Now, we have one problem. The problem is right now, if this top link goes and we lose that AT&T link, the link that I just moved upwards, no traffic will ever reach the cloud for 172.16.0.0. That 172.17.0.0 on the bottom link, it's going to be happy, it's going to be working, it's going to be great. But we lost the link at the top because we lost that subnet. So here's the secret to traffic engineering version 1. Routers prefer the most specific route. That means with the route with the longest subnet mask. So 172.16.0.0 is a specific subnet. 172.17 is a specific subnet. Now, could I actually take the 172.16.0.0/16 and the 172.17.0.0/16 and aggregate those two, or summarize them, or supernet them into a bigger subnet, a bigger CIDR range? Yes, I can, and that's going to be the secret here. So here's what we would do in this particular situation. On the top link, we would put a 172.16.0.0/16, and we would also do a 172.16.0.0/15. Now, if you remember the subnetting workshop we did the other day, you'll see how we did this. If not, my team will pop a link to that subnetting workshop. Please go back to this after the fact. I really want to help you. Now on the bottom link, and why did we do this? Because if this, and we're going to do this on both sides, but for right now, let's assume the Verizon link went away. The traffic on the bottom would no longer be 172.17.0.0/16. The top link would have a specific route to which the route it wants, which is the 172.16.0.0.16. That would stay on the top. But the 172.17.0.0/16 traffic will fall under the 172.16.0.0/15, and then all the traffic works. So by doing this, by taking the top link and the bottom link, and by sending a more specific subnet on that link, and then sending this summary route, often called an aggregate route in BGP, the routers will prefer the path with the most specific links, and traffic will use both internet connections, and we will have no out-of-order packets. That is one way to do this. And what's it going to look like? Here's a graphic that we actually drew for you. You can see on the top link here, this is a little better than my Scrabble and PowerPoint. On the top link, we've got the primary route and the aggregate route. On the bottom link, we've got the primary route and the aggregate route. So now, let's change something different. Chris, you want to pull that screen down for a second? Okay, so now, let's say we want to adjust the weight. Does everybody remember that algorithm we had? Prefer the path with the highest weight. I'm going to say it again. Prefer the path with the highest weight. So now we've got another alternative. Chris, if you could share this slide. Now what we've done in this particular environment, and Mark's going to go build this, and it's going to be fun. On the top link, we have the 172.16.0.0 with a weight of 35,000. The default weight is 32768, but we raised the root weight for 172.16.0.0 to 35,000. We increased it. Now on the bottom link, we raised the weight for 172.17.0.0/16, and we kept the default weight for 172.16.0.0/16. So which link, the top or bottom link, is going to be used for 172.16.0.0? Tell me in the chat box. I want to know that you get it. Which link, top or bottom, will be used for 172.16.0.0/16? The top link or the bottom link? I can sing Jeopardy music if you want. What was it? Do 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 bum 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 bum. I can't completely remember it. It's been a long time since I've had a chance to watch the game. But tell me in the chat. There we go. Chris has got some civility here. Okay, the top link. Preb, good for the top link. Ben, good. Mark, top. Derek, top. You guys are doing great. You got it. I'm thrilled.
Well,
now,
guys, try to be a little bit more specific. When you say top link, try to tell us why the top link. Go through that exercise. Why, not just the top.
Good. Now tell us why it's going to be the top link for 172.16.0.0. Mark and I really want you to get this. It's okay. I'll give you guys a minute to pop it in there. I want you to know why. Good. It's got a higher weight. Excellent. You guys see it. You guys are getting it.
Yep.
And I hope
Perfect.
And I hope you also see that 172.17.0.0 would be on the bottom link because it has the higher weight. Now, remember I said, prefer the path with the highest weight. Prefer the path with the higher local preference. And Mark's going to set this up for you and show you and work with you. But now look at this next one. Here we have the local, we raised the local preference of 172.16.0.0 on the top link, and we raised the local preference of 172.17.0.0/16 on the bottom link. So, which link will be used for 172.17.0.0 and why? Pop it in the chat box. Good. You guys got it. The higher local preference is the reason we're choosing the bottom link. So you see, we could have leaked a more specific route. We could have changed the weight. We could have played with local preference. That's why they call them nerd knobs. We get to get all kinds of geeky with all these kinds of things, and there's so many of these things to remember. All right. Okay, so prefer the path with the highest weight, right? If the weights are the same, prefer the path with the lowest local preference. If the local preferences are the same, prefer the shortest AS path. So what we did here is something called AS path prepending. And what AS path prepending is, we manually manipulate the path by telling BGP to inject extra paths. So you can see on the top link, we kept the original path for 172.16.0.0/16. And we prepended or added an additional AS path of 64523. We know it passed through that autonomous system because we learned the route. It's our neighbor. We just added an extra. Now on the bottom link, what we did here is we kept the standard AS path for 172.17.0.0/16. And we prepended or added or tried to make uglier the weight for 172.16.0.0/16. So now, which route is going to be preferred for 172.16.0.0 and why? Tell me, top or bottom link, and tell me why. Nice job. You guys get it. It is the AS path. Because we prepended those other supernets or CIDR ranges or subnets, any way you want to look at it, based upon your perspective, because your perspective will change your vantage point. You figured it out. It's the shorter AS path. So now let's look at the multi-exit discriminator, otherwise known as the MED. And then we're going to build this stuff out and we're going to get geeky and we'll have some fun with it. Prefer the path with the lowest MED. Prefer the path with the lowest MED. And then we'll take a break for questions. We'll answer some questions. And then after we answer those questions, Mark will build this out. He'll debug it. He'll show you some packet captures. It's going to get real fun real quick. So now we've taken the MED for 172.16.0.0/16 and made it 50 versus the other MED, which is 100. And for 172.17.0.0/16, we reduced the MED to 50. Now, now I want you to tell me both. Which link is going to be used for 172.16 and which link is going to be used for 172.17? And after this, we'll do some questions. Then we're going to get geeky. We're going to go to the routers. We're going to see it. We're going to break it. We're going to have fun with it. All right. Very good. Ed, I know you. Preb, I know you. Ben, Kim, I know you. Great jobs. So you guys are doing great with this. So I love this. So now let's take some questions. Let's answer your questions. You want me to, I can draw out certain things like prepending. If you guys want to see it in real time, we can do it. And then Mark's going to get geeky. And then you're going to see it, and you'll see the routing tables. You can see the BGP ribs and the fibs and all that stuff.
Michael, glad to see that you're here, Michael. Question is, are these attributes changed by us or are they generated by the network? Both. So yes. What you have what they call well-known mandatory attributes, meaning they need to be present and they need to be supported basically by every BGP implementation, regardless of vendor. You have also well-known discretionary. I call them well-known optional, which means they need to be supported by every BGP speaker, every vendor, but they don't necessarily need to be included in the actual update message. So that's those. And then you also have ones, and we'll see especially when we look at the MED, the actual metric, we'll pull up the packet capture. We'll see that there's two additional types. We'll have the optional transitive attributes, which means they don't need to be included nor really supported. But if you don't support them, let's say wait would actually be transitive. It is not, but let's just use that as an example. If it was transitive, but you don't understand it, you would have to pass it along to the next BGP speaker and the next autonomous system so that they can check if that's really for them. That's the type of stuff where communities kind of fall into that equation. And we'll show you later on the actual CLI of what I mean with that. And then you also have optional non-transitive, meaning if you don't support them, drop them, don't pass them along. So those are the four different types that we have. And some of them are by default, they're mandatory, they have to be included. And of course that's the beauty of BGP, right, Mike? You have, yes, depending on what vendor implementation you have anywhere from 10 to 13, 14 different attributes that are pretty standard that you can kind of check on and manipulate. And then depending on what type of implementation you have, if it's going to be an MPLS-based tunnel implementation, there's additional attributes that you can match on. In specific SD-WAN implementations and designs, they took BGP and they added additional attributes to that actual design. So you have even more attributes to match on that you can also manipulate. And that's the whole point about traffic engineering. So BGP is one of those protocols. If you can dream it, you probably can somehow do it. If anyone else will eventually understand what you did, that's going to be questionable.
And you know, I saw 2 questions coming in from Michael, and I know Michael, he's great.
Yeah.
I want to answer both at the same time, but you actually ask now, and the next question, which is related to prepend. So let me go share this my PowerPoint slide, and I'll explain it. So because I think this is going to help everyone. Did I share my screen right or no? Oh, Chris, could you share my screen? Okay, perfect. So let's do this. The internet has always been called the cloud, so we'll call the internet a cloud. So let's say over here, I've got this ISP over here, and in this particular case, the ISP's autonomous system number is 1234, and here's my organization. These are all our data centers combined. This is our private organization. And when we connect to we went to Aaron, we got our, I think it's still Aaron, we got our autonomous system number, and our autonomous system number is 5678. When we have a BGP speaker on these routers, and we form a BGP session, every route that's going to be sent to us is going to have the AS path. It's going to be an AS path of 1234 when we learn these routes. And that's going to be contained by the protocol itself. But we have 2 options in BGP. We could tell this internet service provider, when they send us the routes, to manipulate the route and prepend their own autonomous system number to us, theoretically. And if they would do it, we'd be okay, and that could manipulate our outbound traffic. But what we can do is we can take the route as given to us, which is really how we typically do it. But I'm pretty sure you can do it on the other side. I just never have, because you never trust anybody. You do it yourself. So let's say you learn this route via 1234. You can configure a policy on this router itself. And on that policy, you could have the policy to change the weight, change the local preference, change to prepend the AS path, and you could tell this router when it ejects those routes into the system to have AS path 1234 again. So we could do it on either side. We're going to get these attributes, but we can also tune and modify them. You know, with Cisco routers, we have something called like a route map, where basically you set a list of criteria to do it. We could also receive a community and act on a community, and Mark will show you some communities, maybe like no export and various communities supported in the cloud. You know, this is such important information for a cloud architect or a solution architect, whether it be an AWS solution architect, an Azure solution architect, a Google solution architect. What else is next in questions before we get to the geeky stuff?
And don't be shy to ask your questions. That's what we're here for. We're going to try to take away the angst or the fear, as some say, when it comes to BGP. Like with anything, you do have to spend some time on it. You have to get to know it. It has to get to know you and the fears you have. And hopefully we can squash them a little bit today. But like anything, if you don't know at first, it's going to seem overwhelming. But with time, be sure as you practice, as you try to figure out how do I really make sense of it in my head, you'll see it's not as horrific as, and I hope Mike is not going to hate me for saying this, but OSPF. OSPF is, just from a simple establishment, a lot more complicated than BGP. But question from Hakeem. He says, how does BGP interact with MPLS for traffic engineering and a VPN creation? I'll let you field that one first, Mike.
Okay, so let me draw this out for you. And it's not that BGP really interacts with MPLS at all, but I'll show you what it actually does. Chris, if you want to share my screen again. Oh, I need to share. Never mind. So there's a couple possible VPNs that we could actually do here, Hakeem. The old school RFC 2547 BGP VPN, which was the third cloud that I worked on, really what it did was this. So normally speaking, if we've got an internet service provider, and I'll just let me draw some routers into this internet service provider. It's going to be the world's smallest internet service provider. Maybe we only have 4 routers to make. We'll have 4 routers to make it look, maybe 6, because otherwise it's going to be really too small. So we'll do this. So let's say these are our routers. And I'll draw some links in between these routers. Because we're going to be an internet service provider, we're going to need some redundancy in our network. We'll add this link, and this link, and this link, and this link. So all this stuff is going to sit inside our interior gateway protocol. And let's pop this all into a single autonomous system. So generally speaking, if this was an IP packet, the packet could come in, it would be sent to this router. The router would look in its routing table and say, oh, the next path is to go here, and then the next path is to go here, and then it would leave the network. And it would be an IP packet coming in, and it would be an IP packet coming out. And inside of our autonomous system, we would need an interior gateway protocol, which is going to be OSPF, or it's going to be IS-IS, which is the old CLNS routing protocol. They're going to use one of these two on the way in and the way out of our system. And then what we'd have to do is we'd have to fully mesh our BGP peers. Are we fully meshed right now? No, because we don't actually have a connection between this router and this router, for example. We don't exactly have an extra direct wire or connection over from here to here. And we don't have like a connection from this route. So there's other routers that we're missing to be fully meshed. To be fully meshed, we need n times n-1 divided by 2 connections, which means we've got 6 routers. To be fully meshed, if we're going to do BGP sessions from everybody connected to everybody, would be 6 times 6 minus 1, which is 5, which is 30 divided by 2. We need 15 connections. So we'd have to have BGP fully meshed. Now, if we didn't want to do that, and all we wanted to do was run BGP between these two devices, these two, if we just wanted to run BGP between these two and BGP between these two, we'd break things because we'd be breaking the rules of IBGP. What MPLS enables us to do, though, is we can take our OSPF and we can then turn on another basically routing protocol, like a label distribution protocol, which enables us to switch our data via labels versus packets. And then what would happen is, because you're asking a question that's not really related to BGP, but this would be the packet that would come into the network. As soon as it hit the network, the packet would be encapsulated into a label would be placed onto this. And now what we'd have is an MPLS packet, so to speak, if you will. And then that would be switched across our network with MPLS, label switching versus IP switching. When the router would reach this router, that label would be stripped off, and then the packet would leave the network. So that's your typical MPLS-based VPN. And we could do it via the creation of a pseudo-wire, which Luca Martini from Jupiter came up with. It could be done via VPLS, which is basically a collection of pseudo-wires, which my team at Riverstone was one of the working groups in creating, which is a possibility you could do. Or what you could actually do is you could take the information and you could pop it into something called multi-protocol BGP, which is just an extension to BGP to carry stuff that's not there. And then what you could do is what you would do here is you would basically take the routing information from the client on one side, And then we've got our client router on the opposite side of the system. And they'd be putting the routes into BGP on the way into the network in a special virtual routing and forwarding interface. Those packets would be switched via MPLS across the system. And then that virtual BGP instance on the service provider network would be stripped off, and then the BGP routes would go back to the client. So that was the first of the MPLS VPNs. It had too much BGP in a whole lot of places, and it didn't really serve much of a purpose. So what we ultimately did was we created pseudo wires to create a virtual link across this internet, across these ISP backbones, and we're now just tunneling Ethernet signaling. So I hope that made sense. That got a little geekier than just some of the BGP, because now you're talking about MPLS and various VPLN architectures. We've covered two here: the Martini draft, which became VPLS, and we also talked about the RFC 2547 VPNs.
Yep.
Thank you, Hakeem, by the way.
Great question.
Okay, so now we're going to let Mark get geeky. He's going to set up the BGP, tune the BGP, debug the BGP, capture some packets for you. I'll let him walk you through it. I did my little geekiness talking about the protocol, which is what I love, because for me, I see it all in my mind, but some people like to see it on the screen. So let's have both.
And what we'll do is there's going to be a little bit of housekeeping first. We'll get familiar with the topology. What do we have running on there? Why do we have it running there? There's a couple of things that I purposefully left undone. We're going to look at them. We're going to fix them up, see what we can glean from actually fixing these issues that are in our network. And then what we'll do is we'll actually get into the traffic engineering section of this workshop. We'll go through one, which is going to first start off with our traffic leaking. And then once we're done with traffic leaking, we'll take a couple of more questions, and then we'll proceed on to the next few labs, just to kind of make a point of what Mike was demonstrating early on, how it actually looks on the CLI, the command interface, and what the routers see, and what we can do with traffic. And hopefully we don't break too much on the way too. Otherwise, it's going to become quite a troubleshooting session. So, Mike, if you're good with it, I'll have Chris share my screen.
Absolutely. Get down, get dirty, have fun with this.
All right. So the topology that we're going to be working with, and I'm going to expand this first, is this particular topology. So we'll use the command line. Of course, we'll take a look at what are we running within this autonomous system, the 64,523. We'll take a look at what's going on with 64,501. This particular autonomous system, we designate it as our data center. And realistically speaking, this particular autonomous system could almost be anything you want to. In our case, since this is more cloud orientated, we could say this is going to be, let's just call it this, our C cloud service provider network. Okay. So that's kind of how it's laid out from the foundation. So let's get rid of this and let's start looking at the command line and see what we can glean. Okay. Scroll up. And we're going to start from right and then work our way towards the left. Okay, so meaning we're going to look at this autonomous system. We're going to look at this router 1, 2, and 3 first. We're going to get an idea of where do our routes originate. I wrote a couple of down here just to see what they are, but we're still going to see how they're being advertised. And then we'll see what is broken and what we need to fix to get some basic connectivity up and going. So let's start off with router 1. First of all, what I'm going to do is I'm going to take a look and see what we're running when it comes to IP protocols themselves. So on this particular router, it seems like we're running the OSPF process. We have a router ID of quad 1s. And it looks like we're running a single area, which is normal, just a normal area. So we don't have any of the fancy stub areas or not so stubby areas. We simply have our backbone area, which is area 0. And it looks like these are the particular networks that we are routing for, which is the quad 1 network and the 10.1.0.0. And it's a looks like /16 network that we're running for. So We'll see how that goes. And then additionally, we are running the BGP process as well. And in there, as you can see, we have specific addresses listed as our neighbor addresses, and as well as some additional routing information. So the first thing we're going to do is let's take a look at the other two routers. Then we'll circle back and we'll try to take a look, first of all, OSPF, see what we're advertising, what are we learning, what type of neighborships do we have before we move on to anything else. So let's do the same with router 2. Let's show IP protocols. And it looks like router 2 is also running the OSPF 100 process. Its route ID is quad 2s, and it is responsible and routing for networks of 2.2.2, 10.1, 10.2, and the 172.255 network. So I'm actually going to remove this in a little bit because it should not be there. So we found a little error in our topology. And then we're also running the BGP process. And in this case, it shows us what are we configured for when it comes to our neighbor statement. And we'll dig deeper into the actual configuration, see what this is doing. And then also who are we peering with? Are these actual peerings established? Are they idle? And then we'll go through the actual finite state machine and see what we can see from there. And then also it looks like these are particular routes that we are receiving. So that is router 2. Let's go to router 3. Let's do a show IP protocol. Take a look at the layout of the land. And it looks like in this case, we're also running OSPF process 100. Our route ID is quad 3s. And it looks like we're also routing for the 3 network, the 10.1, 10.2. And it looks like here is more specific. We're actually routing for the 172.16/16 network and the 172.17/16 network. So these are the 2 routes that eventually we're going to be manipulating throughout the rest of the workshop. And then it looks like we're also running a BGP session. So you can tell that we're running internal BGP between routers 1, 2, and 3 within our data center. And in this case, we have a neighbor of 1 and router 2. And it looks like we're not routing for much besides 2 and 1. All right. So let's go back first of all to router 1. And let's take a look and see on what interfaces OSPF is running so we get a better idea, because we want to make sure before we move anywhere or that we move on that our IGP is correct so that we have reachability information available to be able to advertise to OSPF from our internal network. So that's going to be crucial. So let's take a look at our interfaces. Just a quick summary. And it looks like we're running OSPF on our loopback interface. We're running it on our Ethernet 01 interface. So that is going to be the interface from R1 towards R3. And we're running it on the Ethernet 0/0 interface, which is going to be the interface between routers 1 and router 2. And it looks like we also are establishing neighbors on both of these. So that's going to be beneficial to know. And if we want to confirm it, we can just run the show IP OSPF neighbor. And here we can see we are peering, or we have a neighborship relationship with routers 3 and routers 2. We can see that they're in a full state, which is always good. That means that they have converged. They have agreed on all the attributes that are part of the OSPF machine that they have to go through. And they have also, of course, gone through the Dijkstra algorithm and found the shortest path. So that's this first router. We'll go to the second and the third, and then we'll circle back and we'll look at the OSPF database just to get an idea of what type of links are being advertised or being spoken about in the entire domain. So looking at router 2, we're going to do the same thing. We're going to go and show IP OSPF interface brief. Let's take a look what it is running OSPF on. It looks like it's running it on the loopback address, which is our quad 2, which is quite important. We're running it on loopback 172.17. And the important part to notice here that it's down. So we'll have to see why it's down. If we have that loopback address, we'll remove it. And we'll also remove it from being advertised through OSPF because it's not part of this actual router. We know it's part of router 3. But we have a OSPF running on Ethernet, on the interface Ethernet 02, which is going to be between router 2 and router 3. That is this particular link here. And we're running it on Ethernet/10.1 0/0 interface, which is going to be between the routers 1 and 2. So let's take a look here first of all, just to fix this minor. Looks like we do have the interfaces, but we've shut them down. So let's do this. Let's remove it from the OSPF process, because if we don't need to advertise them, we don't need to advertise them. All right. Okay, show IP OSPF interface brief. Let's just make sure we're not running it anymore on this interface. We're not. So as you can tell, if we go back up, where is it? We were originally running it right here. And now when we look further down, we see that it's not part of it. All right, let's see who our neighbors are. In this case, we're neighboring with router 3 and router 1, which makes sense since it's internal to us. We're in the full state, meaning all attributes were agreed upon that are necessary for OSPF neighborship. And we're also exchanging routes, which is beneficial. So let us go to router 3. Let us just do a quick housekeeping there too. Let's look at the interfaces that were part of OSPF. And in this case, you can notice we're running it on our loopback interface. This particular loopback interface is quite crucial, just like on the other routers. We're going to use it for our graph when it comes to OSPF, because we're actually routing towards the node, not the links themselves. We'll explain it probably in a follow-up, maybe OSPF class or so forth, exactly what that means. But just know that in OSPF, we're always trying to solve the shortest path tree towards the node that is advertising particular links, either if they be stub network links or if they be transit links. And I'll show you the OSPF database in a minute so that you understand what that means. In this case, router 3 does own these particular loopbacks, and we see that they're being advertised. We can see that by the actual state. And we're also running OSPF on Ethernet 02 and the interface Ethernet 01, which means that we're establishing a neighborship relationship, meaning we're sending those hello packets out of those two interfaces to see if there's any other OSPF willing routers out there to speak to us. So let us take a look at the neighborship. And here we can see we're running it with router 2, and we're running it with router 1. We're in the full state, and we're exchanging routes. So let us take a look at router 3, because router 3 is a little further into our network. Let's take a look at what his OSPF database looks like. All right. So when we look at it here, we just have one single link state advertisement going out, and this is in regards to our router link state. This just means that we're advertising both our topology information as well as any link information, any routing information. And we see that we received one from router 1, router 2, and then our own originated router LSA, link state advertisement, of course, is there as well. So if we wanted to, let us take a brief look and see what are we actually sending in our router LSA that our other neighbors also will take a look at. So let's see if we can do it this way. So again, this is our router LSA within area 0. So we're not running any type of stub networks, not so stubby networks, or any type of areas that require redistribution. It looks like our link state ID, which is going to be also our router ID, as you notice, is quad 3s. It tells us that we're advertising, or that we're at least connected to about 7 links. So as you can tell, the first one it tells about is a stub network. And the reason that this is a network is you have your actual prefix, and then it provides us with a subnet mask, which is our prefix length. And this particular would then be part of our actual route advertisement. And the same will be true for the next stub network that it's advertising, which is going to be the 172.16 interface, which is going to be our loopback address for that particular network. As we move further down, it's going to be the same deal. Again, this is going to be for the 172.17, eventually /16 network. But the way OSPF actually includes these particular addresses is going to be based on the interface type, which in this case is going to be a loopback address. But BGP is not going to look at it that way. Next, it states we have a link from another router. It looks like it's a point-to-point link, and it tells us the neighboring router has a route ID of 2.2.2, and the router interface address is 10.2.3.3. And then, of course, it provides us a metric of 10. So basically what we're looking at here is that router 3 is telling us about this particular link right here. So that's what it's advertising, or that's what it's talking about with this particular entry. Then with the next one, and let's see if we can clear this up a little bit. Next, we're going to look at further stub networks. This happens to be the 10.2.3. So as you notice, not only did we talk about the link that we're connected to, or that we're using to connect to another router, we're now also talking about the actual route itself, which is going to be the 10.2.3.0, and with a mask of a /24. And as we keep going, the next two are pretty much the same. We have a point-to-point link. This time we're explaining or describing the link between routers 3 and 1. It tells us that the route ID, and that gives you a good idea how OSPF looks at it. It's trying to figure out how to get to the node, and it's telling us this is the interface address associated towards that particular peer. And then finally, we round it up with another network. And this is the 10.1.3.0 network /24. And that's going to be the explanation of, or the description of this particular link. Now, the reason I showed you this router first, even though the OSPF database has to remain the same among the different neighbors or peers within the same interior system to avoid loop detection, you'll notice there's going to be always a little bit of a difference depending on what routes you're trying to tell others about. So what we're going to take a look, and we're going to do this from router 3, we're going to take a look at what is router 1 telling us. And that's going to show you the difference in between. Number one, we're going to know all the different links, both transit and stub networks that are connected to that particular router, but also how we can avoid loops in that sense. So let's go up and let's take a look at the LSA, the router LSA from router 1. So when we look at this, we see immediately it's only telling us about 5 links. So one link it tells us about is an actual stub network, which is going to be the loopback address, the quad once, and it includes a subnet mask. So that makes it an actual stub network. Then it's router 1 is discussing the actual point-to-point transit link. That means between router 1 or itself, router 3 and router 1. So it's describing this basically link again. We have a few additional stub networks. So in this case, it's the 10.1.3.0, which is this. And then here, if we scroll up, you'll notice I was describing, assuming real router 3, I was describing my transit link or point-to-point link between myself and router 2 here. And here we have a little change up. If you look at this particular address, it says the address is 10.1.2.1. So router 1 is telling us about this link right here, the 10.1.2.0/24 network between routers 1 and router 2. So again, you're getting a whole lay of the land in regards to what your entire network looks like, because that's how OSPF avoids loops within the network so that everybody knows every link. And then finally, to round it out, the same network is also described as a stub network by providing us the prefix and then as well as the length. So that's how OSPF is set up. And if we look at the show IP route, and then we'll type in OSPF, we can see this is currently in what we call our RIP, or our global routing table. And we can see as well that we've installed a route towards the 1.1.1 address, towards the 2.2.2 address, and as well as towards the 10.1.2.0/24 network address, or transit link, which is going to be this one. So, and just to answer Michael, just to give you an idea, if we look at our interfaces and what we have configured, I have these particular interfaces configured with IP addresses. And this is where the interior gateway routing protocols differ compared to BGP. So what we're doing here is we're not setting up, and that will make more sense if I show you also the actual configuration. What we're not doing here compared to BGP is all we're saying is whatever our interfaces are, and these are the interfaces that we have configured. These are the IP addresses associated with those interfaces. All we tell OSPF is, I want you to run the process on these interfaces. And that's what these statements are for, these particular network statements. What you'll notice, this is not the case with BGP. BGP will not use multicast to find its neighbor. Again, think of this. If you're trusted, meaning inside of my network, multicast is just fine. I trust you. I'm willing to listen to, if you want to talk to me, I'll listen and we'll establish a session or a peering relationship. But with BGP, this is not the case. We have to manually configure our neighbor because it's an untrusted external source. We don't know what we're going to get. That's why it's quite a complicated process to get BGP up and running, go through different terms of services, especially if we're going to have some type of external route injected, what we want. If we want a full routing table, partial routing table. So there's a lot more that goes into that compared to these. And as we mentioned, BGP will run on top of IP using TCP as its actual, for sequencing, it's going to use it for reliability. So that's what TCP is used for. So does this answer your question, Michael? Can you type in the chat? Does this answer your question where we're getting the interfaces from? So for example, if we're looking at this, the quad threes, it's the same one we have configured here. Okay, fantastic. And just for completeness sake, if we wanted to do it this way as well, this is more of a configuration thing. So this is not necessarily you have to do it or you don't. But let's say if I remove this particular statement, and let's take a look at this, you'll notice we're not running OSPF right now on that particular interface. But what I could do is I can go into that particular interface, which is loopback 0 and IP, and I can just enable OSPF on it. Okay, let's take a look. And as you see, it is back here. So it's just different ways to enable the OSPF process on the interface. You can do it through a network statement, which is different in OSPF and IGPs compared to what BGP is, and I'll show you that. Or you can enable the process directly on the interface. The difference is going to be now is if you look at the actual section of the configuration of OSPF, we'll no longer have the quad threes listed. So you would have to actually look at the loopback interface to see the command. So that would be the difference. So it just depends on how you want to configure it. Okay, so that in a nutshell is OSPF minus the additional going through its actual finite state machine and going into multi-area OSPF. So at least now we know if we look at the routing table at OSPF, I should be able from router 3 be able to reach routers 1 and 2. So if we do a quick ping, I'm going to ping the actual loopback interface of router 1. That should succeed. I'm going to do the same with router 2. And that also succeeds. So we don't see any issues right here. Okay, so that's going to be OSPF. The next thing I want to show you, we mentioned that we're running BGP on this particular segment here between these three routers. So let us take a look and just make sure that our sessions are actually established. So it looks like we are peering with router 2 and 3. We know that as we keep looking further, our session has been up for 2 hours with both of them. We're not going to focus on this one yet, but we're going to focus just on the two. So that's a good way. And an alternative way of checking to see and to garner more information about the actual session is to type in the neighbor address. So let's take a look and see what we get here. And I'll have to add the neighbor statement to it. Okay. And as you can tell, there is a lot of information that BGP will actually give us. So what we're going to do is we're going to scroll up. And what we're concerned about is, number one, is the BGP neighbor ID or the BGP identifier, which is going to be router 2. We're on router 1 right now. It's going to tell us what the autonomous system number is, which is 64,523. And BGP is smart enough to know that I also, on router 1, have the same autonomous system number configured, and it will tell us now this is an internal link. We'll see that it also talks about the BGP version, which is version 4. And what we're really here for is the BGP state, which we see is established. So those are the important parts that we're worried about right now, just to make that the peer is actually up. So let's take a look at router 1, and let's take a look at the BGP routing table itself, the actual RIP for it. So we're not going into our main routing table. That will be the show IP route command. This is our main routing table. It's going to include routes from all types of protocols. As you can tell, we have OSPF-based protocols. The O will follow it up. Here will tell us this is OSPF in the legend. And the B right here, it will tell us is BGP. And that is right here for you. Okay. So what we want to look at is the actual BGP database or the routing table, which is going to tell us what routes it has run through the actual BGP best path selection algorithm, and eventually which routes also will install into the routing table, such as in case of something like this. So in that case, let us run the command. So in this case, what we'll notice is, and we'll get into this in more detail as we go through the actual workshop. So what we're looking at is, it looks like I'm injecting a quad 1 address, which on router 1 is my own. And this is generally designated by the quad 0s as the next hop, meaning it's my route. And on Cisco routers, and such as the case here is, on any locally originated routes, we set the weight to 32,768. And what you'll notice, this is quite high compared to all the other weight attributes that are set. Okay. So if anyone, or if I get a packet for this particular destination, I'm going to use my own internal route. Next, we have a route from router 2, and we got one from router 3. We can tell this based on the next hop. If you remember the route IDs, I have them listed right here. So router 1 is going to have the address of quad 1s, router 3, quad 3s, and then router 2 has the quad 2s. Okay, but we do notice something quite interesting, and that is this particular designation, the R. So if we take a look at that, and let's see, we're going to look at RIP failure. That's what the R stands for. It tells us that the reason this has not been added into the global routing table, that's what we call the RIP, that's why it's called the RIP failure, is that there's something called a high administrative distance. So in this case, since we learned the route via IBGP, because that's the relationship we have, Cisco iOS assigns specific administrative distances. So in this case, an external BGP route that is receives an administrative distance of 20. An internal one receives one of 200. So why is this significant? If we look at the OSPF routes now here, so we got them both. For the 2.2.2, it looks like our administrative distance is 110. Up here was 200. So the low administrative distance wins out. And that's why this particular prefix is installed into the global routing table compared to the IBGP learned route, since it has an administrative distance of 200. And that's what's designated with RIP failure. Okay. Next, we're going to look at it. It looks like we're learning a couple of routes from router 4, which is going to be on this side here. Looks like we're learning the quad 4, which is its loopback address. And then internally through IBGP. And just so you know, if you see this little I here on the side, let me make this a little bit more distinct, this little I, you will notice as you scoot up, we're not talking about origin codes here, but rather what we're looking for is this right here, this particular I, which tells us it's an internally learned route. Okay, so in this case, we are learning the 172.16 and 17 network from router 3. So now at least we know where those routes are originating for. Then we also have RIP failure again to the 192.1.4. If we take a look at where was it at the RIP failure here, you'll notice again, it's a high administrative distance because it's a connected interface. So it carries a low administrative distance. All right. So what I'm showing you all so far, if you want to type in the chat, that also gives me an idea that you're still around and alert. Does so far what we're showing make sense to you? Okay, fantastic. Glad to see, Carlos, that it makes sense to you. Great to hear, Kim. Yes, it is, Michael. I'm showing you a little bit more than what you usually get out of a BGP workshop. This is just to kind of give you an idea of what our topology looks like. I don't want there to be any surprises as we go forward.
Sounds good. And Mark, is everybody with us so far? Do you need any questions clarified by Mark and I real quick? If you do, let us know. If not, make sure you download the BGP document that comes with this, just in case you haven't. Make sure you registered for the free AWS Advanced Networking. And join us on Thursday on the How to Get Your First Cloud Architect Job webinar. It's online. We'll talk about the cloud architect role, what we do, how to get hired, the skills you need. It's free. And then if you've got questions for us about your career, we'll be live on Zoom, and we'd love to help you.
Okay. It looks like from Joseph. He says, why did R1 show autonomous system? And I think you meant to say, well, actually, we don't have 5.4. Oh, okay. I see what it means. Okay. Why did it show as it's an internal route? So this is on R1. Let's do this again. Let's do the show BGP IPv4 unicast table. And what you're talking about is this particular field. So this is one of those little quirks in iOS that I call it. What you only see here that it talks about the path. And generally speaking, this would be considered the neighbor's autonomous system. What they're missing actually is a column, and let me make sure I see my pen, is right here that says origin. So what the I here means is when we look at the origin code up here, that's what this is. This is one of those attributes that Mike was talking about earlier, and we'll go into actually seeing how it's included in the BGP messages, but that's what it's including for. The problem is there just isn't a column, but anytime you see either I here, or what you'll see is the little question mark, that just means the origin of that particular network layer reachability information, or this particular prefix is unknown. And generally speaking, we get the question mark if we redistribute a particular prefix into the BGP process. Does that answer your question, Joseph? I never understood why Cisco never went back and added that particular column in there, just not to confuse everybody. Yep, you see it, Joseph, that's the problem. For example, the version of code that I'm running for these particular routers, I picked them on purpose, also because it just recently came out, is the iOS XE version. And what's really great about that one is, aside from us having to sometimes take a guess at what BGP necessarily ended up used as a tiebreaker for a particular route, this one give you an actual hint as to why a route was selected as the best path, compared to having to always go down to it, because it kind of gets murky, and Mike knows this. Once you get past the med, once the metric is the same, then you're trying to figure out, okay, was it picked because it's an older route, or was it picked because of the route ID? It kind of gets a bit murky in that kind of scenario when we get there. So in any case, as we go through the actual demo a little further, we'll show you that, how this particular version of iOS shows us a reason for that. But don't always expect that if you're working with a network engineer or network architect that he'll use a particular vendor software that will show you that. Okay. And make sure as well that if you like the session, always hit the like button if you haven't already. Give us a hashtag BGP as well, that we know that you're still awake. Okay. So it looks like we got a question from Kovakov. He says, can you please elaborate on BGP multi-hop with this scenario? All right. So we'll have to go a little further. Chris, if you are okay, and go ahead, share my screen again. Okay. So in this case, there is a few scenarios why we might have BGP multi-hop. One scenario could be, let's imagine that there was an additional link between these two routers. And let's say this was the 192 let's call this 4.0. Actually, let's do this. Let's just call this, again, 4.0/24 network. So I have two links now. Normally what would happen is, and I'm going to show you this through a packet capture, is if I did not tell the BGP process in specific to perform the peering through a different type of source, it will always source my directly connected interface. Now, in this case, what would happen is I would have to create two BGP sessions so that I can have them running across this particular link. Now, the problem will be is I'll have two sessions, but if, let's say, this link goes down, whatever traffic was sent through this link simply gets dropped. There would be no way by default that BGP simply says, you know what, I'm going this way, because it's sourcing the actual BGP message off this particular interface. So the way we get around that is, and we have this example of iBGP, is if we take a look at the actual configurations, and then I'll show you where it's actually in the show output, that we set, and this is particular. So just so you understand, I'm running the new address family version. So the top is always going to be your sessions commands, and below it under the particular address family, in this case, we're running BGP for IPv4. Here we're running the actual policies. So in this case, if I'm looking at my connection between routers 1 and let's say router 2, I specifically stated to BGP that I'm looking to establish a neighborship relationship with router 2 who is in remote autonomous system 64523. Well, we know it's not remote because we're running the same, right? So this is the actual check, right? We're running the same autonomous system, so we know it's internal. But what I'm doing is, because I have reachability to this particular loopback address through my IGP, I cannot use that as my actual TCP connection parameter, basically as my destination. And then to make sure that the other side of BGP is going to agree and talk to me, what I'm telling it is, hey, listen, I want you to source my BGP messages from my loopback address, which just happens also to be 1.1.1. So the way this looks, if we go to router 2, is I have just a flipped configuration where I'm stating if router 2 wants to connect to router 1, I'm going to use its loopback address as the destination IP address. And as my source, I want to use loopback 0. So if I'm running internal BGP, what happens is by automatically the time to live in the IP packet is not set to 1 any longer. It's actually set to 255, the maximum. So now it doesn't, as long as I don't have more than, let's say, 255 hops within my internal network, the TTL is going to get decremented as it passes through the routers. So allowing me eBGP multi-hop in a sense. This is with IGP. If I wanted to accomplish the same thing with external BGP, in the scenario that I mentioned where we have 2 links, I would have to also keep this configuration the same, basically referencing my loopback address, stating that I want my BGP packets to be sourced from my loopback address as I'm sending them out. So that's a criteria. But because by default, BGP is going to look to see, are you directly connected or not? Because it sets the TTL as 1. It's going to expect that. It's going to have a directly connected check in place as well. And it's not going to allow that session to come up. So in that case, we have to relax those rules. And what you would then do, and I'll just show you the command, because I have no place to really implement it. But let's say we do this. You'll notice we have either we can disable the connected check, so it's not checking to see or care about the TTL in general, or we can go and just simply configure eBGP multi-hop. And that's going to basically increase our TTL and allow us to have more than 1 hop in between us and the neighbor that we're trying to communicate to and establish a peering session to as well. Let me know, Kovako, if that answers your questions. And Mike, is there anything in particular you want to mention before I move on with the demo?
No, I think you're doing great with the demo. If you're here and you haven't given the video a like, please give it a like. Please subscribe. We'd love to see you back again. And definitely get that free BGP guide and definitely join our free AWS Advanced Networking. We're only 2 CCIEs today, and we've got 3 CCIEs and a CCNP for that one. So we're going to have fun with that.
Yeah. Okay, fantastic. So we'll move on. Oh, okay. Question from Joseph.
Yeah,
can you have a BGP neighborship or peering without a loopback configured on the router?
The answer is yes, but let's talk about it for a second.
Go ahead.
Let's say you've got 2 connections between router A and router B. You could generate the BGP connections on the directly connected links. Absolutely, you could. And by doing so, if you only have a link between router 1 and router 2, and then you are actually going to create BGP over the link, you could do it. Now, here's the problem. When that link goes down, that BGP peering session goes down. Because a link that doesn't have link state, or there it's not attached to the link, when the link goes down, the line protocol goes down, the link goes down, and then the BGP session won't go down. So that's one thing. The other reason we create a loopback, in addition to the redundancy factor, is because the loopback becomes the BGP identifier. And if we know what the BGP identifier is at first, it makes it a lot easier to plan than if we were to just let the BGP identifier be chosen at random to us. So they're kind of the 2 reasons you typically do loopback to loopback for iBGP. For eBGP, you could do it, but if you're going to do loopback to loopback with eBGP, then you have to specify eBGP multi-hop.
That is correct. Yep, because by default, iOS has that, it's checking to see if it's directly connected. We can disable that, kind of get the same thing. But again, now we're looking into, is that the best thing to do? And I'm not talking simply from a security perspective. For security, we're going to use something else, and I'm going to show you what we're going to use for security, because it actually defends against somebody trying to pretend to be a man in the middle and be able to do like a DDoS attack on us, basically trying to overload the BGP process. But when it comes to the actual this check, What it truly defends against is absolutely nothing. But what it prevents is this problem of if our directly connected link goes down, BGP takes quite a while to figure out something is down. And I'm going to show you how we can alleviate that particular problem with BGP. But what can happen is if you have an alternative path to that BGP speaker on which your primary link just went down, BGP is going to source the address from a different link and try to kind of loop around and get there. So we don't necessarily want that to happen, because then BGP can become non-deterministic. And what we want with BGP, think about it. What's the whole point of it? We're trying to scale to the level of the internet. That both means with IPv4 prefixes and IPv6. So I think last time I checked, we had probably close to, what was it, like 900 plus thousand IPv4 addresses, and IPv6 is slowly catching up a little bit with that too. I think it's anywhere from 3 to 500,000. I don't remember the top of my head, but that's where you want stability in your network. Otherwise, you got to go in there and you got to add some additional things like dampening in case some neighbor has this issue where they're always going up and down, or something happens to your prefix that you're learning and that goes up and down. So that is one of those things that we want to keep in mind.
Yeah.
So, but if you have redundant links between you and your service provider, listen, you want to take advantage of it. What you do is you do the peering on the loopback address, because that one is a logical interface on a router that will not go down unless the entire router goes offline, meaning it shuts down. So that's also a viable option. And do we have any further questions? Okay, fantastic. All right, Mike, if you don't have more to add, I'm going to pile on a little bit on what the topology is and what we got cooking.
Pile on and have fun. I'm loving this.
All right, fantastic. All right, Chris, if you wouldn't mind. Awesome. All right. So now I got to remember, what did we all cover? So we covered our interior gateway routing protocols. We covered that they're configured right here with OSPF area 0. And that's going to be between routers 1, 2, and 3. We also are running iBGP between them. And what we want to just take a quick glance at is, what is each router advertising? Just so we get an idea before we move on to the next network and see what's going on. So we're going to start with router 1 first of all. And what we can do is we can do a show BGP IPv unicast, and what would be a good way to show you guys this? Yeah, let's just do it this way. So I'm advertising, because I can see I'm the next hop, the 1 network, and that's about it. It looks like it, and we can confirm that too if we look at the configuration. As you can, and this is particular what I was talking about. In OSPF, we use the network statement to enable the process on the interface. In this case, what I'm saying is I actually want to inject this particular prefix into BGP, and that's my actual loopback address. Okay, so that's what we have. And aside from that, we do not have any additional injections. And for those that care, this is the particular security command that we put in line. Is this TTL security hops 1, which sets the TTL at 255, and the next router expects to get the packet with a TTL of 255, because if it's going to get decremented to 254, which means it cannot be passed on, thus always having the directly connected check in place. But this is a security mechanism, and it's going to be very difficult to hijack the session this way. So in any case, that's router 1. Let's take a look at router 2. What are we running with, or what are we doing with BGP? So it looks like I'm the next hop for 2.2.2, and I don't see any other next hops. So it looks like this is all we're going to be injecting in BGP, and it looks like that's it. Again, just our loopback address. Let's take a look at router 3. Okay, so here we got a little bit more. So it looks like router 3 is the next hop for the quad 3 address, which is going to be our local loopback address. It's also the next hop for both the 172.16 and .17 network. And again, we can tell that by the fact that it's the next hop right here. And if we had access to look at the configuration, and in this case, the configuration is not that large itself, we can see that we injected the 3 network and we've applied a subnet mask to it because it's not a classful address. And on the other one, since they were /16, BGP knows that these are going to be /16. We don't need to include the actual subnet mask. And it looks like we're injecting them as well. Okay, so from that perspective, we have a very simple IBGP configuration here as well. And it looks like router 3 is going to be our main go-to when it comes to applying basically policies when it comes to govern these particular 2 networks. Okay, so I'm going to do one more final check here on routers 1 and 2. I'm going to see what type of sessions they have configured, and then we'll move on to routers 4 and 5 and get into taking a look at the finite state machine of BGP. So let's do a show BGP IPv4 unicast, and we want to do a summary. And it looks like, just as we discussed, router 2 and router 3. And when we scroll over, we don't have anything listed in the state section, which means we have a peering establishment. And it looks like we also have something going routers 192.1.4.4. And that looks like, if this is router 1, that we have a peering relationship towards this side. So that's what this one is. So we do have an eBGP peering already established. So to confirm, let's take a look at that neighbor and see what we can glean. So in this case, I'm being told our BGP router identifier, also known as our router ID, is quad 1s. Our local autonomous system is 64,523. So that's what we have configured. It looks like I have 8 network entries. I have 11 path entries. And as we scroll further down, we're also going to see that this is an external link because the remote autonomous system number is different. So again, that's the check that BGP will do and how it figures out if it's internal compared to an external link. The most important aspect here is we want to see that it's an established state. In this case, it has been up for 1 hour and 53 minutes. We also can glean some additional information, such as what is our default hold time. It's 180 seconds. So that gives you an idea how long it takes for BGP to actually go down, 3 minutes, if it does not receive its keep alive, which is 60 seconds. So in that case, if I miss 3 keep alive messages, those are going to be those messages that I'm checking, are you there, are you there? Or in the case of when we're doing the initial establishment of peering, are kind of like a, do I agree? It's almost like a synchronous kind of acknowledgement message, probably is the better word to use, compared to TCP as well. What else do we have cooking here? Let's take a look. We're running BGP version 4, so that's good to see. And it says we have 1 active neighbor, and it says multi-session capability is not enabled. So that's a good thing too. And we get an overview of the different messages that are being sent, how many were sent and received. As you can tell, a lot of information here as well. We're not going to go through necessarily the capabilities, what they are. They might change, but I'll show you the actual packet captures of where you'll see this capability exchange. This is done in the open message. The routers will need to agree on these capabilities, otherwise they can't form a peering. And there's other things such as the BGP version, as well as there cannot be a duplicate router ID. That's also going to cause problems. And of course, our autonomous system needs to be correct because of the configuration statement that we have. The one thing that I do want to point out, this is something nice, is where is it at? Let me see if I can find it. Is this particular section here. It will tell us that the TCP session must be open actively. So I'll go into that later what this means, but here we actually see the TCP session. It says it's established. We have a minimum incoming TTL of 254, and for outgoing sessions, it's 255. Okay, so that's the security. Also here, it gives us a hint, who is the client and who is the server. So basically, who initiated the session and who listened for the session. So what we're looking for, if you think of the client and server model, is the client is going to pick a higher, or we call them an ephemeral port number. In this case, it picked 19,766. And it's going to send its message to port number 179. So in this case, this is the port number that BGP listens on. And we'll see that in a minute also in the packet capture. So this is really good to see that we have this ability within the actual BGP show command to see the information about the TCP sessions, because we can't always do a packet capture. So this is pretty good to see what was negotiated. Okay, so that's with router 1. So we know there's at least a session between router 1 and router 4. And let's take a look at router 2. We won't do the same thing. Let's just do a quick summary to see what sessions we have enabled. There's a session between router 1 and with router 3. We see the autonomous system. And if we were to do any troubleshooting, these would matter as well. That means in what input and output queue the actual messages were. That could give us some type of idea if there is a problem with just general transport when it comes to IP as well. The next thing you want to see is what is our state. In this case, the state is established, but because we don't see it here, we assume that it's established. We see prefixes that we've received from these neighbors. And what we want to focus on is this particular neighbor here is the 192.2.4.4, which just happens to be that router 2 also has a session built to router 4. Okay, so from our data center so far, we got 2 external sessions built. One from router 1 to router 4, and from router 2 from our data center to the remote router 4. So at least we know what's going on. What we can do, and this is just as bonus, is let's take a look, and we're going to take a look and see what routes are we advertising. So that's going to be now my RIP adjacency out. So these are these logical databases that BGP builds. It can build a RIP adjacency in, so that we can we can look at the routes that we're receiving before we apply any policy. We have our main RIP from BGP, our BGP RIP. That's where the best path selection already ran, and those are the routes that we're going to install in our global routing table. And then we have our adjacency RIP out, and that's the routes that we have gone through the policy application already, and that we're going to send to our neighbor. In this case, we want to see what is being sent to router 4 from router 1. So let's take a look. So in this case, it looks like we are sending the 1. We're also sending the 2 and the 3, and as well as the 172.16 and .17. So it looks like we are already sending the /16s to router 4. And that should also be the same if we take a look on this link. Oh, here we go. So I was on router 1 here. This is router 2. And we can see we're pretty much sending them the same thing. The next hop might change a little bit. What I do want to point out just briefly, pay attention to this. It says the next hop is actually the loopback address of router 3. So I just want you to keep this in mind, because that tells us that when router 4 goes to resolve, it may have to figure out how to get to this. But we'll take a closer look and see what our configuration tells us on the other side. So let's take a look at router 4. And we're going to quickly go through the same process as before. We see that we're running OSPF, process 200. Our router ID is quad 4s. And it looks like we are running the OSP process for this particular network, the 4.4.4 network, and the 10.4.0. So let's scoot over a little bit so we can see what's going on. And that's this particular interface that we're running OSPF on. And then we're running also BGP. And that explains, of course, how we had those external sessions. Let us take a look at briefly, what are we doing with OSPF interface-wise? So we're running it on our loopback, and we're running it on our Ethernet 0/1 interface. So the loopback and this particular interface. And do we have any neighbors? We do. Looks like a neighbor with the ID of quad 5, which we're going to make the assumption is router 5. We're also in the full state. Quickly take a look at our database. That seems to be pretty simple. We're going to look at our own actual LSA, our router LSA, just to see what is included. And in this case, you can tell it's quite small compared to the others where we had 5 and 7. In this case, we're just talking about a stub network, which is going to be our loopback address interface, the quad 4s with a quad 255 network mask. We also are going to describe our point-to-point link, which is going to be the 10.4.5.0/24. And here we're actually providing the actual network. So we have topology information, and we got route information for that link. So far, pretty standard. Let's take a look, because we said we're running BGP on this, right? Yep. So let's take a look and see what type of BGP sessions we got running. So right now, it looks like we're only running BGP with routers 1 and routers 2. So one of our goals in a little bit is going to be to establish an internal BGP session between routers 4 and 5. To answer your question, Michael, the router ID is not actually, it's an identifying number. And it generally is a 32-bit decimal number. So what you'll notice in instances when you're running any of these protocols, but for IPv6, your router ID is still going to be that 32-bit decimal number. So it's always going to look like an IPv4 address, but it's simply there serving as a actual identifier. Now, in the case of OSPF, the router ID, in this case, we use just a consecutive string of those numbers, quad 1s, 2, 3, 4, and 5. That is actually, that particular address needs to be routable. Thus, we're using the loopback address because we're not routing to the actual networks. We're routing to the node that claims to advertise those networks. So in that case, if let's say router 1 is advertising a particular topology information, including the networks, in this case, it was quad 1s, I'm not trying to figure out how do I get to, let's say, the network 1.1.1, but I'm trying to figure out how do I get to the node that owns that network. So that's where OSPF is quite different compared to either like ERGRP or BGP. They actually go by what the next hop address is to get there. Yes, and router LSA is a type of link state advertisement or link state advertisement that has this topology information and the actual network information. But that's only for IPv4. When we're dealing with IPv6, OSPF version 3, that particular information, topology, and the actual route information or the link information is separated. So there are two different LSAs at that point. Okay. So, but what we want to briefly just focus on is we have the actual external peering sessions up. So what that should mean is, and let's take a look, what are we learning through OSPF here? It looks like we're only learning the loopback address of router 5. Let's see what router 5 is learning, the OSPF. Seems like only the 4 network, and let's do a complete show of the routing table just to kind of see what's going on. Yeah, so router 5 is not learning a lot. It looks like just the loopback address and the rest are all connected links. What about router 4? Let's take a look here briefly. Okay, so router 4 is learning some BGP prefixes that it then injected into the global routing table. It looks like we're also learning about the loopback address of router 5. And then, of course, the 2 particular networks, which we'll take a lot more interest in shortly. So does anyone have any questions so far when it comes to this setup? And then we'll take a look at what options we have. I'm going to throw a little like impromptu bonus in. I hope Mike doesn't mind. but I'm going to do a quick redistribution of some prefixes because I want to briefly talk about that it is an option, but that you don't want to do it when you're distributing from BGP into IGP.
Sounds great. Before we get to this for everyone, for those of you that desire to become cloud architects, the good news is we don't ever have to touch this technology. We're not going to be looking at the routing tables. We're not going to be looking at the LSA tables. We're not going to be looking at the BGP rib or the BGP fib. We're going to be just thinking of how the protocol works, how we design it, where our BGP peering points are, and maybe how to traffic engineer it. The rest of that is for the wonderful engineers that get down and dirty every single day. When it breaks at 3 o'clock in the morning, they come in and do it. They think about all the things here. The first hour of this session, that's the architect piece. Mark and I want to give you an experience so you can see what the engineers do, so you can see what it looks and feels like on the router. Architecture is conceptual. Engineering is all practical. So keep that in the back of your mind. You don't have to know that. You have to just know the first hour for the architect.
And to answer Michael's question, in this particular demonstration, yes, the consecutive ones, consecutive twos, basically the quad, I've chosen them just because it's easily identifiable for me in regards to this route ID. But what you'll notice too is can you quickly just share my screen, Chris, so I can show them? We take a brief look here. What you'll notice is that, for example, in this case, for our external BGP neighbors, I have not overridden anything when it comes to their actual router. Well, actually I have. I've hard-coded the route IDs. But when it comes to BGP, notice what it says that it's actually peering to. Those are the interface, directly connected interfaces. So it uses them to identify the neighbor on the actual CLI. The BGP identifier is used in the actual BGP messages now for different purposes. One of them will be in the open message to make sure we don't have the same route ID. And then depending on if we're doing any type of route reflection, anything where we might even have clusters, we'll even have a cluster ID, which is going to be the BGP identifier as well. Okay, and if you want to go back to me and Chris, not me and Chris, Mike and I. Yes, so in this case, the router LSA is a type 1 OSPF LSA. So depending on which implementation you have, you can probably go up, I think it's like 9, if I remember correctly, especially with IPv6, which is OSPF v3. All right, so Joseph asks, why is R2 using R3 as the next hop router in the IP BGP summary statement to reach R4? I don't think I saw that. You said this was in the summary, right? So Joseph, I'm not going to have Chris change it. I'm going to show you a little bit, but just so you know, when we're running this particular summary command, so when I'm doing, you can do either show IP BGP summary, or in my case, I'm using the more address family friendly syntax. All I'm looking for is what is, no, you don't need to change right now, Chris, just leave it. When you look at the summary statement, all I'm looking for is what established peering sessions do I have. If they're not established, it will tell me that they're either going to be in idle, they're going to be in the active, or the connect state. So sometimes if you're quick enough, which I'm not going to be, it's quite difficult. You might even catch it in something like an open send, open confirm state. So in any case, that particular show command only shows me at that time what is established or what is pending peering. But it has nothing to do with what the actual next hop is to that particular prefix. But we're going to get in more detail in regards to the next hop, how it's viewed, what happens when it becomes inaccessible, why it becomes inaccessible. But we'll tackle that in a little bit. I'll let you answer this one, Mike. A little OSPF. It says, if you don't manually configure your OSPF router ID, then it will use the highest loopback address on that router as the router ID.
That's typically the default with a Cisco router.
Yeah. So, and if you don't have a loopback, it's going to be the highest interface IP address.
Yes.
So in this case, again, when it comes to any type of routing, especially routing protocols, what we're trying to do is we're trying to design it with enough so that we can determine it as much as possible. We don't like undeterministic outcomes. So in case of, like, for example, the BGP, OSPF, the route ID becomes the node identifier. And the graph that the Dijkstra algorithm eventually runs through to find the shortest path is actually graphing to the node, which is going to be that OSPF identifier or the route ID. You don't want to leave that up to chance, because think of it this way. Can your interface go down? Yes, it can. Okay, if that interface just happens to be the highest IP address on any interface, guess what's going to happen? OSPF is going to reset itself. It's going to tear down all my different neighborship arrangements. And in this case, we're only running 3 routers. You're going to get a lot of side eye if it's 100, 200, or 300 routers that just went down, because you have to pick a new route ID. Then you have to tell everybody else about that. Then they have to run the Dijkstra algorithm again to find the shortest path to the node. And then they need to install all those prefixes back into the OSPF database first. They need to tell about each other, so you have a huge flooding event, which nobody will love you for. And then eventually, maybe, if you have no other problems, you will be in a full state.
Exactly. So think about this. During that time, all these LSAs are being sent to every other router because one thing changed. If you've got 1,000 routers in OSPF domain, which is not a lot, all 1,000 routers are going to have to recalculate the routes. If those routers happen to be busy because their CPU was busy because somebody sent a broadcast or they were forwarding too many traffics or had too many services turned on, now those routers crash during the recalculation, and then they have to reboot. And nothing works during the reboot. And what happens after the reboot? Then all these systems have to come up, and then they start flooding LSAs. And in poorly designed OSPF environments, where people leave these things up to chance, and they don't summarize between boundaries, you get one little link that flaps up and down. It can take down an entire network. And the key here is, automatic, auto magic, that's not really what we want. We want to plan it ahead of time. So we can plan it, we can calculate it, and we know where it's going to fail, how it's going to fail, and we can engineer that traffic. So that's why, we architects have to look at this big picture. What are we trying to do? What kind of things do we have? And we have to work with engineers. We have to, because they're going to be the people that are going to be down and dirty in these routers. And when there's 1,000 of them, you're going to need more than one engineer. You might need 30 of them. And they're going to be dealing with these performance tunings up and down. And, we need that collaboration between the architects who focus on the business and these engineers that are really great technology professionals.
Yeah. So again, you want to be as deterministic as possible. You want to bake into your actual design or your network it to be stable. That's what makes BGP so great. BGP, unlike a lot of the IGPs, it doesn't have these odd events where it just maybe every hour or so floods its entire routing table to the next peer. You can imagine, and I'm going to be kind here because we know they're getting close to about like 1 million different IPv4 addresses in the routing table. What if we only take 500,000? Let's say I ingested into my domain 500,000 different routes or prefixes, and one of them flaps, goes down. Guess what? I have to wait for the withdraw message. So I'm going to get an update message. Within that, it's going to say that it's a type of a withdrawal. It's going to give me the prefix, including the length. Then I have to withdraw it. Depending on how I have my BGP configured, I might have a repair path. Maybe I don't. So now you got to churn through the entire actual BGP best path algorithm just to see if there's anything else. And then if you have any downstream routers, guess what? You'll have to send them the same update message with the withdrawal type code in there so that they also do the same. So you have some weird kind of like daisy chaining, but that's one prefix. What if 500 just vanish? It's not going to be a fun night if you get called. Try to figure out what that is. So just keep that in mind. Try to be as deterministic in any design that you have as humanly possible. There's not always, when you're not always going to be 100% on. Remember, design is always going to be a give and take. That's why we say it depends. We're never going to be able to match everything 100%.
You know, that's an important thing to talk about. It's a give and take. Here's what we think about architecture. Everything we do that helps something is going to hurt something else. I want to make the convergence faster, I lower the timers. If I lower the timers to make the convergence faster after a failure, I may overwhelm the CPUs. If I overwhelm the CPUs of the systems and they crash, I've got absolutely nothing. So we're always in this dissemination of what we do. More security breaks things, but if we don't have the security, we could get hacked. So the way we would think of what are we securing, what's the value, what's the risk financial-wise, what's the risk quantitatively, and make our determinations. And then a good architecture is one that evaluates all the trade-offs and makes the best decision for the business, not the tech, but the business. Which one best helps the business? And that's why mainframes are making a comeback. That's why private clouds like Nutanix and OpenStack are growing, and people are leaving the public cloud for better, faster performance at a cheaper cost. And yet they're still going to the public cloud for some of the great things the public cloud offers, because all this tech has the ability to change things. We just have to put the right tech. But if you were going to build a house and you used a saw when you were trying to, what do they do? A hammer to put a nail in? You know, the saw wouldn't be a great job of the hammer. The hammer does a good job for the hammer, and the saw is to cut wood or whatever the people do with saws. I'm not mechanical at all. I always respected people that are, but I'm not. But, you know, that's the thing. We have to use the right tool for the job.
Yeah. All right. If there's no further questions, what we'll do is we're going to take a look at seeing if we can reach from one end to the network of the next. And we're going to do a little demonstration of redistribution and start talking about why it might be beneficial not to redistribute your BGP into your IGP, so to say, and rather to use something like iBGP because of the way that the message is sent around and its scalability, functionality, and you get to keep those wonderful attributes in place that you can actually do traffic engineering or manipulation on intact as well.
Okay, so I want to make sure you're still awake, that we didn't get too geeky on you. So if you haven't given the video a like, please like it. If you like it, if you don't like it, don't like it. Subscribe to the channel and hit the bell to be notified of new videos. And, you know, give me a hashtag that shows me you're awake. Hashtag BGP. I'll do it too.
And you guys are doing fantastic. We get it. It's a lot at once. You know, champions aren't born overnight. You have to work for it, but stick with it. I know I saw a question earlier about somebody, how would they practice this? We don't necessarily provide the configurations when it comes to the routers themselves. But what we would suggest you do is there's enough information on the actual topology and what we're running through right now that you should be able to rewatch this particular session, which we encourage you to do anyway, and then be able to recreate this. Now, there's going to be a few things. Let's say that if you don't have one of these, I don't want to call them some premium emulators, but let's say you can run EVGN or EVNG community version, which is going to be free. You will have to figure out how you gain those images, the router, the firewalls, and so forth to run this topology. Same with GNS3, the free version. You can do the same thing, but you'll need to get the images. I'm not 100% sure exactly what is and would not be supported when it comes to Cisco Packet Tracer. When we later on look a little bit into the best path selection and how IOS XE shows us which path was chosen as best or not, that is not going to be a supported function in Cisco Packet Tracer. Just a little heads up. But you should be able to re-engineer this topology by yourself, no problems.
Absolutely. And we have to determine the difference between knowing it and being able to build it. You can enter configuration commands all day long and never know it. I interview people every day that have done thousands of labs and know nothing when I ask them how to describe it. Knowing how these protocols work, you have to read the RFC. You have to watch or read the training that teaches you how the protocols work. When you know that, then you can just build it. but if you want to, but you have to unknow it. And this is not the kind of thing where you're going to learn how the protocol works, what an open message does, what an active transition is by configuring it. I wish you could. You just can't learn this by doing. You have to learn this by learning it. The Internet Routing Architectures book from Bassam Halabi is great. Routing TCP/IP volumes 1 and 2 from Jeff Dial are fantastic. The IETF RFCs, which are free, are phenomenal, and you got to read all of them. And I guarantee you, Mark read all these books and RFCs. I know I did. It was required for every CCIE. In fact, they would give you the configuration guide on the CCIE.
Mm-hmm.
Here's your commands. Here's how to configure everything. And yet it still had an 80 to 90% failure rate because you had to know what to configure. And when they would say, make sure this link was used over this link, they needed you to know the BGP decision tree. And then they needed you to know which attributes you can do. After that, being able to look at the commands, that was the easy piece, but it was knowing what you needed when you needed it.
And then we're going to come out. If they just tell you directly what they want you to do on that type of exam, I mean, within enough time, anyone would be able to do it as long as they at least have, an understanding of the particular protocol.
Yes.
But what made it particularly challenging, and I think that's where sessions like these are great, you can have the free BGP guide that we have, which has the decision tree that BGP goes through up. I, for example, have that up as well. There's also a Cisco version of that. Let me do this because I'm going to put this in the chat so you guys have it. So this is from Cisco. And what you can do is, as you practice and as you study, there's no shame in having it in front of you. If you take a CCIE exam, then mnemonic is going to be your best friend. We love oranges as oranges mean pure refreshment. And then you do translation, what is a weight, the local preference, right? And so forth and so forth, so forth. So you unfortunately do not have the particular steps it goes through on the CCIE exam. I think that's where the real gotcha gets to. And think of it this way. In a real design, and when I mean real design, I mean if you're actually doing an implementation either in your lab or for a real customer. Let's say you're doing that. Having all these attributes at your disposal is a godsend. It's fantastic because you can manipulate the way traffic goes in and out of your actual autonomous system at will. And you can match it on whatever you like. But you got to remember the order, because whatever order you do the actual change of the attributes, another attribute can override it. Give you a simple example. Think of weight. Weight, if we're using a Cisco implementation, is the first attribute that we look at. If I, on the other end, though, I selected, let's say, local preference, weight will override local preference any day of the week. That's how it is, because it's high in the decision process. So that's something that you would have to pay attention to, exactly what kind of attribute you're changing. Again, real life, fantastic. On an actual CCIE exam, that's where the nightmare begins, because they can change any of it and they can ask you to change any of it for a particular outcome. So if you ever do go for one, just hope they're not going to be as predominantly heavy on the BGP part, and maybe they'll bless you with OSPF.
Yeah. Mohammed, let's talk about that BGP black hole question you're actually asking about. So let's talk about what black holing traffic typically is. And there's a time where you want to use, and there's a time where you don't.
Yep.
So a black hole is typically when you send traffic to a location that you don't have a route to, or that doesn't exist. So if I said that I own the route to 1.1.1.1, and I don't, and I send it to null zero, or a place to drop the packet, and I advertise to the entire internet that I have a route to 1.1.1.1, and and it was coming to me because I had the best path, all that traffic would be destroyed. Now imagine this. Now I imagine that there's a hacking event that's trying to get to a certain thing, and it's coming from a specific IP address. I can literally black hole that traffic. I can create a route and send all that route to a dead location so it can no longer be used to hack me. Black holing could also be not that you intentionally made a route go to the wrong location, but either you have a route to it and you don't have a route back, so your traffic goes nowhere. But it's really dealing with if you don't have a route or the reachability of something, and you think you do, but you send it to a place where you don't get there. It's kind of like, it's really what it is. That's all.
Yeah, and what Mike was talking about, just put in chat, you can do it purposefully. It's called a remotely
Yeah.
triggered black hole. So this is an additional defense mechanism against a denial of service attack. And it is a little bit more broad. You can couple it or integrate it with BGP FlowSec, which is going to look at the individual flows and allow you a bit more granularity in regards to what you purposefully would black hole. Now, there's also another black holing, and that is when you're terrible at your aggregation. Meaning, if you have not learned how to do supernetting and you send out a shorter prefix length, and that encompasses networks you don't own.
Yep.
So what's going to happen is it's going to come into your router. Your router is going to do the lookup. And if it does not find a more specific route, or worst case scenario, a default route, it's going to black hole the traffic. And that's also how big BGP outages can happen when somebody inadvertently, or let's say even maliciously, and again, that's where that route validation would come into place actually, black hole traffic on the internet.
Yep.
If you do it on purpose, you're not going to have a good day at the office. Let's just put it that way. All right. If we don't have any other questions, then I think it's going to be time to do the demonstration in regards to can we reach from one end to another, and then do some redistribution. If you're good with that, Mike.
Sounds good.
All right, fantastic. Chris, if you wouldn't mind sharing my screen again. Okay. So what we're going to be attempting is to send traffic from router 3 to router 5, or from router 5 to router 3. And in particular, what we're going to be looking for is being able to reach the loopback addresses on either of these devices. So the first thing that we're going to do is we're going to go to router 3. And what I want to do is I want to do a lookup in both the BGP RIB and then our main RIB table, our global routing table, and see, are we learning the prefix 5555? If we're not learning it, that means it's not being injected. We may have to move up a hop and see if we need to test to router 4 first. So let's take a look at our routing table. So in this case, it looks like I'm not learning a 5, but I am learning a 4. And if you notice something, is we have these greater than signs. And looking up here tells us that this is selected as a best route. So it looks like we'll have to figure out before we can even get to router 5, excuse me, why we can't get to router's 4 loopback address. As you can tell, there's no greater sign. It says, it looks like we're learning this through iBGP, and our next hop is 192.4.4. So that looks like we're talking about these two interfaces. So apparently what we're being advertised, we cannot reach. Let's take a look and see if that's the case on the edge routers, routers 2 and router 1. So in this case, all right, it looks like we can reach the next hop of 192.1.4.4. And our best route happens to be through the directly connected link between routers 2 and router 4. Let's take a look at router 1. And in that case, it looks like we also have the 4 route. It is designated as a best route through our directly connected link. So that's this particular link. And just in case, if we wanted to, we did not install it into the global routing table, but we do have another route to that same prefix, the 4.4.4, through router 2. And it tells us this was learned via iBGP. So the first thing we need to see, what is BGP telling us in regards to, on router 3, why it's not even bothering running the best path selection algorithm. So with that, let's pull up the actual route and see if we can figure this out. Okay, let's take a look here. So I'm not actually looking at the details of the route. So it's first going to tell me that I have 2 paths available, but no path is the best path. All right, so we got path number 1, we got path number 2. And it looks like this path we learned from router 1. And it says, oh, look at that. It sent us this particular route with the next hop of 192.1.4.4. Now, this is quite interesting because router 2 does the same thing. As we can tell, it says from router 2, but once again, it tells us this particular neck hop, and then here is what we're looking for. It says inaccessible. Now, here's the interesting part about when we're advertising an eBGP learned route through IGP, and we don't change the next hop address. It's going to make the assumption for loop prevention as well that we should have a route to this particular next hop. So in this case, on router 3, we can look at our routing table, and let's just take a look for this particular route. What does it tell us? No route. I'm going to look at my cache and see, just in case if Cisco Express Forwarding maybe is having some type of default route or anything for this prefix, so we're not confused. And it looks like it's telling me I have no route. And that should differ if we look at something, for example, like router 1. Let's do this. So in this case, it looks like we are installing it. See, do we have a route? We do. It tells us it's learned via BGP. It provides an administrative distance of 20. It looks like we learned it from the neighbor 192.1.4.4, and it's providing us with the next hop of 192.1.4.4. So let's do a lookup on that particular address. Can we get there? Yes, we can. It says via Ethernet 01. So by the way, this is also demonstrating to you what I just did. I did a recursive lookup. So to be able to get to the loopback address, I needed to figure out who's advertising it. And then that peer had to tell me what the next hop address was. But then I had to figure out, how do I get to 192.1.4.4? So I had to perform another lookup. This is called a recursive lookup. And there I find out that I have a directly connected interface, which is Ethernet 1/1, that I can use to get to this peer. And in Cisco iOS, we happen to have the option of actually taking a look at the Cisco Express Forwarding table. And that's where we have the pre-computation, where it tells us, for this particular prefix, your next hop is going to be 192.4.4.4, and it's going to be out of interface Ethernet 1.1. So again, it's very important, not just for BGP to be able to install the route into the RIP, that is the routing table, to make sure that the next hop is accessible, but as you can tell, at times there can also be a recursive lookup to get us to that particular route. So the first thing that the things that we now need to figure out is, if router 3 has no idea how to get to the loopback address of 4, what are our options to do so? Now, we have some options where, for example, if we wanted to, so one of the options would be is to take these transit links and inject them into our IGP. So that would be one option that we can do. The next option would be to run iBGP between our neighbors internally and advertise the actual transit link. Now, we can do one or the other. Personally, I always go for best practice, and I rather run IGP, because then I'm not mixing externally learned routes into my IGP, which can bring down the performance depending on, how large my actual injection of routes is. And I'm also separating my internal domain to my outside domain. And of course, if I wanted to, also keep the attributes around in case I wanted to extend my network. I have multiple exit points. So in that case, injecting them through the network statement in the BGP process would be more desirable. But let us take a look and see what we can do on router 1 first. Okay. So it looks like I have a path to 192.2.4.0 via 192.4.4.4. Okay. So this particular injection doesn't help me because I'm trying to actually resolve to this particular next hop. So it looks like I'll have to actually inject this particular prefix into my BGP configuration. So let's give that a shot first and see if that happens to resolve our problem. So in this case, I'm going to inject the 192.1.4.0 network. I'm going to add a mask of a /24. Okay. So if I do a lookup of my BGP table, it looks like now I'm injecting into the BGP process this particular transit link, and it says I am the next hop. Okay, so let's take a look at router 3 and see if that changes anything. Okay, so let's take a look. Oh, there you go. Does everybody see this now? That we have a valid best route to 4.4.4. And look what it says. It still says the next hop is 192.1.4.4. You still see that? All this simply because we are now injecting and advertising a transit link, an external transit link. So let's take a look at this prefix just like we did before. So what you'll notice is it will tell us that this is our AS path. Actually, let's start at the top. There's 2 available paths. Path number 1 is best. The reason it is, number 1, it's actually accessible. Unlike the second route where it still tells us it's inaccessible. Looks like we were applied a metric. Here's our origin of IGP. Here's our multi-exit discriminator. It currently is set to 0. So if you don't define it, they're always going to be set to 0. Our local preference is set to a 100. It tells us that this is a valid route. It is an internal route, and it's best. Okay, and then as you can tell here, and I'm going to show you this now. This is a function of iOS XR and XE, where we can run this command, and it will actually tell us that the first path is the best. It says overall best. And then when we look at the next option, it says this is not the best because the next hop metric is inaccessible. So here at least we know directly from the BGP process why it did not select this particular route as the best route. So this should mean now that it should install the route of 4.4.4.4 to be accessible to the next hop of 192.1.4.4 in my main routing table. So let's take a look. Okay, and here we are. It says 4.4.4. It is internal BGP. The administrative distance is 200, and it says via 192.4.4. So if I do a show IP route for 4.4.4, again, this is the actual logic behind the routing and why it's important to understand that BGP only provides you the reachability information. It does not dictate, or rather, it does not actually provide you the routing capability itself in this case. So the quad 4s is learned via BGP, is what it tells us. We know that it's distance 200 and then it's internal. It says we learned it from 1.1.1.1, and 1.1.1 tells us that 192.4.4 is the next hop. Now here's the thing. Before I get to 192.1.4, I may have to look up how do I get here. So if I do a show IP route for this particular IP address, I learned that it's via OSPF. I learned it from router 1, and my next hop to router 1 is 10.1.3.1, which is going to be this particular link. And we see also here via this particular interface. So then I would have to do a routing lookup on this. And again, I find out that this is a directly connected interface, and it's out of Ethernet 01. And then the final show is via IPsec. And now let's see what we got. And it tells us to get to this route, your next hop, meaning from device to device, is this next hop to Ethernet 01. Okay, so as you can see, again, there's multiple steps in looking up a particular route. All BGP does is provide us the information. How we get there is going to be internally up to our IGPs until we get to the edge of our network. And then what we do is we're zoom out, meaning we're not looking at the details anymore of neither autonomous system, but all we're trying to figure out is what direction towards which autonomous system do I need to send the packets. So in either case, we do know that we have a route. So what we're going to do is we're going to send a trace route. We want to see what type of path we're taking to the 4.4.4 network. And we're going to source it from our local loopback interface 0, which is going to be the quad 3s. And the reason we're doing this is if I'm looking as to how router 4 would respond to any traffic coming from router 3, we need to have a route to router 3. So in that case, the only address I know about from router 3 is the loopback address. And that's why I need to source my pings from the particular address. Okay, so let's take a look if that works. Let's wait for it to complete. Okay, so in this case, it's telling us we made it to 10.1.3.1, which is going to be the Ethernet 01 interface on router 1. Then we're going to use the transit link, which is going to be this one out of interface Ethernet 1.1 towards router 4. And then all we see that the next hop was basically that interface IP address, which is Ethernet 1.1.1. And to confirm, let's show you guys this. Is right here. Ethernet 1/1 with the IP address of 192.1.4.4. Okay, does everybody see how crucial the next hop is when it comes to BGP and its resolution? If you just want to type a yes in there in the chat box, that'd be great. And while I wait you guys' follow-up, if you have any questions, type them in. What I'm going to do is I am going to inject also the transit link while I wait for you guys into my domain on router 2, just so that we have 2 available routes that we can choose to when going towards the loopback address of router 4. So let's take a look here. All right, Chris, I appreciate the music. It's quite soothing. If nobody has any questions, just briefly show you guys, we injected this particular transit link into our IBGP process that we have between router 2 and 3. And as you can tell now, we have 2 available paths. Path 1 is still the best. And in this case, it tells us it is because router 1 has the higher, or it says has the higher router ID. Now, I don't want to confuse you guys and be like, oh, okay, well, isn't this the route ID? Well, we're looking at the BGP process here. Right, so that's how it kind of figured out that this is the best path for this particular prefix. And if we do a show IP route BGP, This is our main table. And in this case, what we're doing, we're actually multipathing. Not to confuse anyone, but the reason I enable multipathing, which is also a attribute of BGP characteristics, is so that we have both paths available from the actual internal routers. This is not on by default. Okay, not to confuse anyone, you can see it right here. I've enabled it. If I disable it, okay. You see, this quickly changes, right? Actually, it's right here. So let's put it back for all intents and purposes, show IP route BGP. And here we are. We got both paths in there again. Okay. So in this case, we now have reachability from router 3 to router 4. What we want to work on now, though, is taking a look and see what's going on. Let's remove this. Between routers 5 and 4, and see if we can at least maybe inject or try to get to the route ID of router 5. So let's take a look here. And if I recall, we did not run any BGP sessions. That's correct. So in this case, if we look at the routing table, and we're going to look at the BGP fib first, okay? If I can type. It looks like we are learning about the loopback address of router 3. So this is now where we have an option again. We can run iBGP between routers 3 and 5, and then inject this particular prefix into our iBGP session so that router 5 can learn it, and then we can do the routing. Or alternatively, what we can try is we can try to redistribute the loopback address of router 3 into our OSPF process, which then gets propagated to router 5, since router 5 and 4 are actual neighbors. So we're going to briefly do this, and just understand this is not necessarily best practice to do it in this fashion, but it is an option that you have, is to redistribute BGP into your IGP. So let's take a look here. What we're looking to do is we're looking to inject this particular prefix, all right? So I'm going to do a sloppy way. I'm just going to inject everything BGP into my OSPF process. So to do that, I got to go to my OSPF process, and I'm going to redistribute. And as you can tell, I have quite a few options to redistribute. I'm going to take the lazy route. I'm just going to redistribute BGP just like this. And it's going to be process 64501. That's going to be my autonomous system number. And I'm actually going to leave everything here the same, except I'm going to do subnets. And I'm going to leave it there for a second. Okay. I'm going to look at router 5 again. And if you recall, this is what our original routing table looks like. So we knew about the loopback address of router 4. This is our own loopback address. And then outside of what our link was between them two, we didn't know anything. Let's take a look and see if we know anything else. So I'm going to show IP route to see at our global routing table. And here we are. So it looks like now we know about the 1 network, about the 2 network, 3, 4, of course, 5. And it looks like we also learned about the prefixes, the networks from our data center, and also the transit links. So this again shows you that, we can do it this way. But again, this is not the best way of doing it, because the IGPs are based on performance. So we want them to route as quickly as possible to the nearest exit to our destination. So we want it to be quick, and we want it to be optimal. But that also will come with a performance hit when we're injecting a lot of routes into it. Other ways to do it, depending on what protocol you have, is you can do summarization, such as with EIGRP. OSPF, you can do also summarization, but you have to do it at border routers. So in general, with OSPF, you're going to create a hierarchy through different areas. So basically, think of them like choke points. So if that's the case, let me take a look. If I do a show IP route for the loopback, It tells me I'm learning it via OSPF. I don't want you to worry about type 2 versus type 1 externals. That's just basically means how the metric is being counted. But what we're looking for is to figure out, I need to get to router 4, and it looks like my next hop, at least for this address, is going to be the 10.4. So we're going to take a first look. What is our route towards router 4? I know it's kind of oxymoron because we only have one link, but it tells us it is also via this next hop. Let's take a look. This next hop we're directly connected to, which means if I do a lookup on my final destination, it's going to tell me to get to 3.3.3, use the next hop of 5.4 out of Ethernet 1. Okay, so let me take a look now at router 3, just to make sure. Show IP route. And let's see, do I know about router 5? I don't. I only know about router 4. So that means if we ran a ping to router 3, even sourcing our loopback, and let's say repeat 5, this should fail. Okay. Let's do a trace route towards 3.3.3, and we're going to source our loopback. So it looks like we're making it to router 4, and then traffic is dying. Let's look at router 4. Well, it definitely knows about it. Okay. So the problem here is going to be we don't have bidirectional communication because router 3 has no idea about the loopback address of router 4. So here's the nice thing about BGP. If we look at our routing table, we learned the loopback address through our IGP. Since it's in our routing table now, our main routing table, we can inject it into BGP, and that way we can provide reachability. So let's take a look at this. So we're gonna route a BGP, and in this case, it's 64,501. We're going to do address family, and we're just going to do a quick redistribution of OSPF process 200, and that's about it. Okay. Let's take a look. And here we go. Now, this might be a little bit of a problem later on. We'll see if it is. But in any case, let's go back to router 5. Well, let's see if we can reach it from 5 to 3. And look at this. Here we go. We're going to router 4. From router 4, our next hop is going to take us to router 1. And from router 1, we're going down to router 3. So in that case, we solved our reachability problem through the redistribution into our IGP from BGP, and then also advertising the particular loopback address into our BGP process. So does anyone have any questions so far about this? Because we're going to slowly start picking up the pace. I just want to lay the groundwork. And not sure if you want to get myself and Mike back on the screen in case we have any questions, Chris. I'm mute. So, question from Joseph. Since BGP is not a dynamic routing protocol, then how does it find its next hop router in order to direct the packet through the thousands of routers within the internet to reach its destination?
And BGP is a dynamic routing protocol. You don't have to statically configure it. It learns it. Now, here's where you typically get you hang up on the next hop not being reachable. So you're connecting your autonomous system to another provider's autonomous system. And that link in between you and the internet service provider's autonomous system. That's typically where you get in trouble. And why is that? Because on all the links in your internal network, you're running your interior gateway protocol, such as OSPF. But on that link between you and the internet service provider, you don't want to form an OSPF adjacency and take their IGP routes inside of your autonomous system. So there's a couple ways you can work around this. Option one is, let's say you're using OSPF as your, your interior gateway protocol. You can take the interface that connects you and your internet service provider and create what's called the passive interface, which means advertise it into your IGP, whether it be EIGRP, OSPF, what have you, but don't form an adjacency. So that's one option. The other thing we used to do is we would either create a static route to that next hop or redistribute a connected subnet to that next hop, and then we would advertise that into BGP, and then it would be reachable. That's typically where you get into the BGP problems.
Yep.
But it's a great question. And that's the one that I remember on the CCI exam always getting me.
Yeah. And I want to point out to you, Joseph, think of it this way, what we said earlier. Your interior network is trusted to you, at least when it comes from a router perspective. That's why we can use such thing as dynamically finding our neighbors through multicast. Because what's going to happen, a routing protocol like OSPF is going to listen, just like BGP listens on a port on a specific IP address. We call this a multicast address, so that many can talk to many. It's going to listen to them. If it hears somebody wanting to establish a peering relationship or a neighborship relationship, it does so. It doesn't question it. Now, of course, you can set up authentications and passwords to protect the session. But in general, as long as you're internal, I want to talk to you. BGP, once again, we're connecting our internal domain, our private network, to an external entity. That is an untrusted network. That's a public network. Think of it this way. Would you connect your internal network without any precautions, without being able to granularly control what you send and what you're willing to receive with anyone on the internet? Unless you want to find a new job. At that point, it doesn't matter if you're a technician, engineer, and architect. You're going to have to find a new job. So that's where you want to take the differentiation. It is a dynamic protocol, but it gives you granular control over your policies, at least from how traffic leaves your network. That's where it's really good at. And to a certain extent, also how we can influence traffic returning. But the important part is we want to control what is coming in when it comes to prefixes and what we advertise as well. Because remember, just because you think you're a trusted source, the other side is going to view you the same way you're going to view them, as somebody they can't trust immediately.
Exactly.
Okay. So again, it's a relationship that's initially built on not trusting each other. And over time, at least with your service provider, right, you go through the entire contract, you fill out what you can do, what you cannot do, what is supported, what is not supported, and so forth and so forth. But always think of this. An external BGP session is always connecting to an untrusted network.
Good questions.
Okay.
I like when people ask questions like this. So it's up on the screen, so I'll bring it up. Join us for the free AWS Advanced Networking. It's going to be next weekend, Friday, Saturday, and Sunday, all day, every day. And it's going to be some geeky folks. We're going to have some fun. We got a couple of 3 CCIEs. Benedict is also, he's a CCNP. He's a real rock star. Going to make sure you guys understand it. Me, Mark, Mo, and Benedict, we're going to have lots of fun. So make sure you join us. Do you have other questions for us?
If you don't have any other questions right now that you might want to ask, I'm going to start getting into the actual finite state machine. And we're going to, from now on, we're going to start moving a little forward with more rapid pace. So just a fair warning. So I'll give you another maybe 15, 20 seconds if you want to ask any questions. Otherwise, I'm going to put my engineer hat back on and then try to transition engineer architect, give you guys an idea what are we doing, why are we doing it.
Absolutely. And at the end, if anybody wants Cindy photos, I'm always happy to share my famous cat, Cindy.
All right. So how do they do in auctions? Going once, going twice?
Sold.
Sold. All right.
First,
we get fair warning. Let's get back to the topology and let's get a little geeky again. All right. So the first thing we're going to do now is, because I definitely don't like this solution of redistributing BGP into IGP. And well, IGP into BGP is not horrific if we control it, but we have a better solution. And that's actually using IGP to proliferate or to disperse routes from external entities into our network without impacting our IGP performance. So what I'm going to do first is I'm going to undo the additions that we made, which include the redistribution statement under our BGP process, and then, of course, the same for our OSPF process. So let's get rid of this first. And let's do this. And where was it? Here. And then finally, we'll remove this particular statement as well. And to confirm, this should be easy enough. We go to router 5, show IP route, and we're saying again, right? So we moved away from, where is it at? From this, where we injected all the routes, to just a normal routing table, okay? So now what we want to do is, and let me move this over first. We want to create an iBGP session. So we want to do iBGP between these two routers. So let us take a look, first of all, and see what we have configured so that we don't redo our work. So we're going to start on router 5. I want to take a look and see under the BGP configuration, what do we got? Okay, so we're invoking the BGP process. We're hard coding our router ID to 5.5.5. We are logging neighbor changes. Since this is just what I've gotten used to, I've disabled the default address family of IPv4, meaning I have to manually tell the router I want to run IPv4. I right now already have neighbor statements. So I have a neighbor statement to router 4. It looks like I'm going to use my loopback address as the source for my BGP messages. And this particular command forces router 5 not to initiate the actual iBGP session. So this is just something that we can control the actual connection state and the active state. So, and aside from that, we are injecting our loopback prefix, and just like on router 3, all we want to do is, again, by default, we only can use the best path as it is given to us by BGP through the best path selection algorithm. But what I want to do is I also want to use all the paths available to me. So I ran the maximum path iBGP command to allow me 2 routes. So let's take a look at router 4. So in router 4, it looks like we do have the configuration already set up for router 5 as well. We're telling us that it's going to be an internal session based on the autonomous system number. We're also going to use our loopback address to source our BGP messages. So that's going to be necessary, considering that router 5 is going to be looking for this to be the source in the BGP message. Otherwise, it will drop them. And then just to force router 5 to be the active seeker of the BGP session, we have this command in there. And then aside from that, it looks like that's about it. So, all right. So in that case, let me take a look here. I believe, let's do this. I believe this is router, this is a packet capture. So this is router, yep. There we go. So let me close this up. So this is router, we can see it right here. So this is the source address. So at least we know where, get my pen, there we go. So at least we know we're on the right segment between routers 4 and 5. And this is the multicast address I was talking to in regards to OSPF, but that's besides the point. Okay, so I am looking at, it looks like the right capture. Okay, so what we're going to do is I'm going to enable the neighbor on router 5 first. And we're doing the peering towards router 4 with this loopback address, so we're going to activate it. Okay. So we should notice, see, that's a different link. Okay. We should notice that there's no TCP handshakes trying to be initiated. We don't see any type of BGP messages, regardless if they're an update message, a keep alike message, we see nothing. Let's take a look and see if the BGP summary statement shows us anything. Oh, here we go. So it says neighbor 4.4.4, autonomous system 64501. And now notice this. It says state idle. Okay, so now we're looking back at the finite state machine where we had the state of idle, we had connect, open send, open confirm, and establish. So in this case, it shows us we're basically just waiting for a start event, something that's going to trigger us to go through the rest of the finite state machine. In our case, we forced router 4 to do the initiation, so we'll get router 4 configured. But in the meantime, we're running the packet capture, and I actually want to do a packet capture also on, an actual debug on router 5. Let's see what we get there. On router 4, let us go ahead and enable the actual BGP session. And remember, we got to peer towards the loopback address, and you'll see in the packet capture why that's important. And we're simply going to activate it. Let's see what happens. And let's hope that I was capturing on the right interface. It looks like I was. It looks like our adjacency is up. Okay, let me take a look and see what we captured here. And it looks like we did capture a few packets. So let's see if we can do it this way. Nope, that's not the command. Is it this? No, maybe it's not. Let's see if we can do this. We do a TCP and let's open it up. And let's say that we want to apply, we want to select it. So we're going to add it, and we want to select BGP as well. Apply, and let's say, and select it. Okay, and that should give us a little bit of a cleaner view. All right. Before we look into packet capture, let's look at the actual debug. Okay. So the first thing I'm going to show you is a show, and I think it's TCP brief, if I remember. Yep. So again, our local address, this is on router 5, right? It says is 5.5.5, and we have port 179, and that's because of the passive command. We became the server. Router 4 was the initiator, the client, and it's binding its loopback address to this particular port number. So this is what we call the socket, and this is also what the TCP session is going to be set up on those loopback addresses. And then finally, we see that the current state of TCP is established. If we look at BGP, we also notice that this particular neighbor now, we don't see the state as before where it was idle, but we did receive a prefixes. So that's good news. So let us look, first of all, see what happened. So in this case, we see that we went from idle to connect. So we had a start event in BGP, which prompted us to move into the connect state. And as we mentioned, the connect state is generally where we're looking to set up our TCP three-way handshake so that eventually, as this handshake completes properly, we can move into the BGP sessions. So just as a side note, I generally look at it this way. There's a phase 1, which I call TCP, and then I consider there to be a phase 2 of the BGP relationship, which is BGP. It is Within this context here, where we're looking at idle, and then it can either be connect or active. We generally always start off with connect, where we're trying to establish a connection to our peer or we're listening for one. If this process fails, we'll move into the active state, which means that we're actively seeking somebody who wants to talk to us, another BGP speaker, but we're still open to listening for incoming requests to talk to us. So that is that particular phase, the way I look at it. And that's kind of like also what you see happening right here already with the connect state. The BGP phase, what I call it, is where we're going to have the open send message or the state. Then we're going to move into the open confirm. And then finally into the established state. So, and this is particularly good to remember in case you're ever being asked about it on a test, if you have to do any type of troubleshooting, if you have to be the architect to actually guide and coordinate troubleshooting sessions. These are good ways to keep in mind that to establish a BGP peer, there's two distinct phases. One of them has to do with a TCP, where we have to be able to establish a session or this point-to-point session through the TCP configure session parameters, which is going to be our actual source and destination IP address. And then to have an actual finally stable connection with BGP, we need to go through these particular stages or states before we can even advertise any kind of prefixes. So if you guys want to write that down on a piece of paper, just as a reminder, you can. Otherwise, you're always welcome to review the session to kind of keep in mind that you can break it up in two phases. Okay. So in this case, we moved from idle to connect. As was explained, we had a start session. Now I'm listening and looking for another BGP speaker. As I move down, I should see that we received an open message. So that tells me that at least at that point, we didn't actually log everything. It looks like it, but we'll have to see how it goes. That we received an open message. So at this point, there's a few other things that we do in regards to capability exchange. Again, things that we support, that we don't support, that the router has to make sure that both BGP speakers understand. And let's take a look if we can find how we're moving. And here it is. Here we're moving from the connect state into the open send state. Again, that's because the open was sent. And now that we're in the open send state, what is happening is we're listening for an open message from our peer. So that would be the next state. Once we have received an open message from them, we're going to check it against the mandatory requirements, and that's such as the BGP version, the BGP identifier, which is the route ID. What is the autonomous system that you're telling me that you're in? Because if that's incorrect, then I can't actually continue with my peering with you. I will move from the open send state back into the idle state, and then I'll move into the active state to see if I can bring up another BGP session to you. So that's what happens in the open send. Once you receive the open message from your peer, and once you've gone through it, you're going to send a keep alive, which is basically going to acknowledge that your open message is okay. I agree to the capabilities. I agree to the autonomous system, your BGP identifier, etc. And once that happens, I'm going to change my state from open send to open confirm. And then the other neighbor is also going to do the same thing. They're going to send a keep alive once they've reviewed the open message, and they're also going to move into this particular state of open confirm. Now, here's where the little tricky part comes in. Many people expect that once we sent the open, it was confirmed, why don't we just move into the established state? Again, the open send and the open confirm is basically just to confirm that we're willing to talk to each other. Then to move from open confirm to the established state, we're going to send another keep alive message, basically saying, now we can go ahead and talk. And once that is received from one side, this does not have to happen simultaneously. we will move to the established state. And that's where we are now willing to exchange prefixes. Now, in our case here, and I'm going to move back here, what happened was on the router, actually it's on the router 4. Let's take a look there. I have network statements advertising routes. So if I didn't have these, I would not be able to send them on or inject them into the process, meaning that I would have 0. So again, this is one of those things, keeps in mind. Just because the session is established, I'm speaking BGP with you now, doesn't mean that I'm going to have automatic routes. This is, again, that trusted was untrusted. You want to granular control what you're going to inject into your BGP session. So that, in a nutshell, was the finite state machine. But let's take a look at the actual messages that went on between the two speakers and see what else we can glean, okay? So as you can tell, there's a little out of order because we have quite a lot of packets. We're at packets 4,823. But the first one we're looking for is our TCP SYN message. So as you can tell, this is TCP. Let me whip out the pen. And there's quite a few important things. The first one I want to point out, look at our source address here and look at our destination address here. So these are the loopback addresses that were configured on both routers 4 and 5, and they were part of the update source, as well as what address we're looking to peer with our BGP speaker. So as you can tell, this is included in the actual IPv4 header as source and destination. So if this was not expected by either side, we would move from, actually in that case, we would not even get past the connect state, and we will move back to idle, because this was not expected. Okay, so that's an important part as to why both the address we're going to use to peer on and also the address that we're going to source our updates from are quite important. Next, we can see that our source port is an ephemeral port, which means it's just a random high port number of 47,000, but our destination port is 179. So this is the port in TCP that's going to listen to our BGP messages. And then finally, this is going to be our SYN, and that's going to start the 3-way handshake in TCP. And that's also basically was a start event in BGP eventually. So let's take a look at the next couple of messages and see what we can glean. So we moved from a SYN from router 4 to router 5. Then it looks like, this is a little bit out of order, we are looking for a acknowledgement back. So it's a little out of order. Let's see if we can just do it this way. Okay, let's see what we have. We got a SYN, we got an ACK, and it looks like we're missing something here. So let's do this. Want to back to where we're at. I'm just going to do a clear of the session because I actually want to see the messages come in. All right. Looks a little bit better. Okay. So we got our SYN message here. We got the acknowledgement from router 5 to router 4 of our SYN message. There's the acknowledgement. And then router 4 here is acknowledging that they're willing to continue. So this particular portion had to happen. That was our initial state, the idle, the connect, and the active, to be able to move to the BGP, the phase 2, where BGP sends its open message. So now looking at the open message of BGP, we notice a few things. First of all, it tells us that the message type is an open message. Here are the things that we're going to check for. We're going to check for the BGP version, which is going to be version 4. My autonomous system, which is 64,501. So again, that's going to be part of that configuration where we'll tell it what remote AS the other router is going to be in. The hold time is included. Now, this is a negotiated value, meaning whichever is lower, that's the one we're going to use. Our router ID, also known as the BGP identifier, is included, which also has to be unique. So these are the main things it checks for. And then we have to agree on capabilities. Now, there's lots of different capabilities. So as you open them up, one of them you'll notice is the multi-protocol extension. So in this case, it tells us that it's going to be for IPv4, and then the subsequent address family identifier is going to be for unicast. Now, let's see what else we got in here. So this is route refresh. Okay, let's look at this one. It tells me I support 4-octet autonomous system capability. Again, this is important for backward compatibility in case there was a router that only understood the 2-octet autonomous system instead of 4. So that's important. And here you'll see also it talks about, again, the autonomous system number of 64,501. So this in a nutshell is the BGP open message, which if you looked, you'll see portions of it on router 5 when it speaks about, it's right here. See, version, hold time, option parameter lengths. You'll see here it talks about multi-protocol extension capability. So we can see this also in our debug as well, just the same thing. Let's take a look and see what other messages we are including. And just as a side note, Mike, is there anything you wanted to add to this particular open message before I move on and take a look at what other messages we got?
No, I think you're doing a great job summarizing that.
All right. In that case, let's take a look what else we got. So in this case, it looks like router 4 sent the open message to router 5, and router 5 sent one to router 4. And then it looks like router 5, so now we're in the open send state, is going to confirm the open message from router 4 by sending a keep alive. And just for those that are wondering, the keep alive is literally just this. There's nothing else into it. It's just to let you know, yeah, I'm still here. I agree, and moves on. And the marker, in case anyone wonders, this is a legacy marker. It used to be, I believe, used for some type of authentication, which is not being used for anymore. The actual authentication is now done through the TCP options. But I digress. So router 5 sends a keep alive to router 4. It's going to move into, it's going to wait also for the keep alive from router 4 to router 5. Both routers at this stage are going to move their BGP state into the open confirm. And then, as we mentioned, we're, well, basically, well, some we're missing, but we basically have keep alive messages that move us into the established state. Then what we're going to happen is we're going to receive an update message. And this update message, as you can see, is can be quite verbose. There's quite a lot of things in it. We're going to open up the first one here. And let's take a look, because we're going to start having our path attributes included. So we have our marker, what type of message code it is. We also have path attributes. So this is where we're now looking at something such as an origin. As you can tell, it says IGP. Then the other mandatory attribute that needs to be included in every update message is the AS path. In this case, it tells us the AS path is 64,523. Our next hop, which is going to be our next mandatory attribute, is 192.2.4.2. So again, for those that were asking, the next hop attribute is included in the actual update message and is mandatory, meaning it's required to be supported and to be included in every update message. Next, we have multi-exit discriminator, which is set to 0. And then we also now have a, by the way, this is a optional non-transitive attribute. And I'm going to show you as well as right here. So we can see that it will tell us that this is optional, non-transited, and guess what? It was not dropped, and it was not also chopped up in multiple update messages. To compare that to something like our, let's say, next hop attribute, you'll notice that in this particular case, this attribute is transitive. It is also well known. Now, just so you know, anything that is well known automatically is transitive, which means it's going to get passed along to the next autonomous system. Okay, let's delete that. And then finally, in this case, we're also including our local preference, which is a well-known, and it says transitive. So a local preference generally is known as a well-known discretionary attribute, meaning it does not have to be included in every BGP update message, but it has to be supported and it has to be passed on. Okay, so here we have several attributes that are included in this open message. You can have less than this. Sometimes it's just the origin, the AS path, and the next hop, since those are mandatory. And other times, depending on the actual implementation of the vendor operating system, you may have more. And then this is the interesting part too as well. We'll look at the network layer reachability information. And just to prove it, again, it's just the prefix and the length of the prefix. In this case, this is talking about the loopback address of router 2. When we open up the next message, the update message, we see, again, it's an update message. We have several path attributes. As you can tell, in this case, our next hop is 192.1.4.1 compared to 192.2.4.2. And let's take a look. What are we advertising? We're advertising the 3 network. Again, 3.3.3 with a length of 32. And then here we're advertising the 172.16/16 and as well as the 17. So does anyone so far have any questions in regards to this? All right, if there are not going to be any questions, what I'm going to do is I'm going to move on and give you guys a quick little bonus, and then we'll do the actual, I know it's been a long time coming, the actual traffic engineering. So one of the things I wanted to show you, just to kind of round it up when we're talking about actual convergence, how quickly things go, is that by default, BGP has quite a long hold time. We mentioned it was 180 seconds. So if we look at router 1, for example, and we look at it at its peering relationship with router 4, it tells us that the hold time is 180 seconds. So that's quite a long time, which means if I did this and I moved to this particular interface and I shut it down, my local BGP process would immediately go down because I wouldn't get the actual carrier signal anymore on my interface, so it knows it's offline. But I want you to notice something interesting here. I did not receive such a message, a syslog message on router 4. And if I take a look at my BGP summary, oddly enough, if you notice, this is still kicking. The 192.1.4.1, which is router 1, this session from router's 4 perspective is still there. And just to prove it, let's take a look at the actual neighborship and see what it tells us is going on. So right here, look at this. So even though the interface is down on router 1, we're not going to have to wait 3 minutes for the process on router 4 to figure out that there's something wrong. So we want to speed this up a little bit. So the way we can do that is to provide a failover mechanism through the bidirectional forward detection. So this is a little bonus for the session. We'll quickly configure it. Just a little teaser. This is how active it looks on a packet capture when you have BFD configured. So as you can tell, it's a lot of messages. We're about 141,000. I've been running it since the beginning. But let's get it configured between these two peers. So the first thing we want to do is, number one, make sure, did I turn the interface back up? Let's do that first. All right, let's wait for our peering to come back up. Okay. And let's do this. I want to say this is this interface. All right. We should have up here. Let's see if we can find it. See, we never got it. So let's go back down here. And what I'm looking for is, let's see if we can find it. And it looks like this might be it. So in this case, it is an update message. But this one I wanted to show you. Where we're drawing routes within the update message. So just a little thing to keep in mind, that there's not a separate message that is being sent out, but that the withdraw is included in the update message. Here's another update message. Let's take a brief look at it. It tells us it's an update message, and here we're actually advertising some additional routes. Okay, so that all looks good. Okay. Okay, and let's just make sure this peers back up, which it is. So, and we have to do this on both sides. So let's go to interface E01. We're on router 4. And I'm going to set up BFD. And what I'm going to do is I'm going to set up an interval of 500 with a minimum receive of 500 milliseconds. And I'm going to multiply it by 3, which means about a minute, about a second and a half. And as you can tell, it's going to get turned on. The next thing we have to do is towards the neighbor. And again, this is going to be part of the session, right? We want to enable BFD. And we do this through the fall over command. And then we designate what we're going to use. In this case, we're going to use BFD. And the reason we're going to use bidirectional forward detection is a very light protocol, and it can do sub-second convergence of neighbors. So let's turn this on. And at this time, it looks like our neighbor is still down. So let's go do this on the other side as well. Okay. Okay, and it looks like BFD is up. Now what I want you to see is the difference. If I go into the interface on router 1, the one connected to router 4, last time we saw router 4 stay up while router 1 went down. Let's see what happens this time. Okay, so we see that router 4 went down. It sent a reset message. So we should have seen that. Let's take a look. And let's take a router 4 here. And notice this. It says neighbor, it's actually right here. Neighbor 1.4 send the reset. And then the neighbor session went down. So if we do a quick lookup, what do we notice? Okay. So that's a actual mechanism that we can use. So Chris, do you want to bring me briefly on screen? Okay. So is everybody still around? Do they understand what we just did? We just actually tuned BGP for fast convergence. If you're still around, type in hashtag BGP.
Yeah. If you're alert and oriented and awake, give us hashtag BGP. We know this stuff can get pretty geeky and pretty deep. And we're scratching the surface on BGP today. We love it. This networking thing can be really fun if you love networking. If you don't love networking, we can get pretty geeky, pretty deep, pretty fast.
Yep. So again, if you just look at it, we're doing a little bit tuning of BGP. We've established a session. A lot of it, we threw you guys a bonus in regards to how the topology is set up, why it's set up the way, showed you a couple of use cases. If Mike is okay, I would like to move on and we'll work on the actual traffic engineering.
Why not?
It shouldn't take us too long. If you all would like to still see that happen, let me know in the chat.
Let us know.
There you go. All righty. So let's do this. Chris, if you wouldn't mind, go ahead and share my screen. And we're finally going to move on and do some traffic engineering. Okay. So our first case of traffic engineering that we're going to be doing is we want to send a aggregate route, meaning when it comes to the actual network that we have, the prefixes here, we are going to do the following. On the top link, this is what we'll call it, top link. So we'll call this top. Actually, let's do this. Just make it simpler. We'll say this is a 1, this is a 2, and we'll say link number 1. We're going to try to shoot for the following. We want to advertise the 172.16.0.0, and this is going to be our /16 network. And we wanted to also have a aggregate route of 172.16/0/0, but this is going to be a 15. So this is going to be a route that is shorter, and it also would encompass this 172.16 and .17 if they were not around. On the bottom link, which is going to be link number 2, what we want to see a final product is to see the route 172.17.0/16, and we want to see the aggregate route, which is going to be the 172.16.0.0/15. Okay, so that's what our intent is going to be. So the first thing we're going to do is let us go to router 4, because router 4 is the one that's connected to both data center router 1 and router 2. Let's take a look at it and see what it's learning right now. So right now it looks like we're learning the 172.16 network from router 2, and the same with route 172.17. So one thing I'm going to do, let me take a look here. Okay, that looks all good. Okay. So that's what I'm learning right now. The best routes, I have no alternate, which is quite interesting. We have this. Okay, so that should be okay. It's interesting that I'm only learning it this way. All right. So what we're looking to do is on the top. So the first thing I'm going to do is I'm going to find who owns these particular prefixes. In this case, it's router 3. So on router 3, I'm going to show you the option that I personally would go for, and that will be in generating an aggregate route, suppressing the more specific prefixes, and then leaking them to the proper neighbors. So this would look something like that. So I'm going to go into my router BGP configuration. And what I want to accomplish first of all is send an aggregate route. And in this case, it was 172.16.0.0. And if you notice, I have to provide it in a dotted decimal notation, which means it's going to be a 255.254.0.0. Now, the first thing I'm going to do is I'm going to leave any additional options off this command, just to see what would the result be. Let me take a look at our local BGP RIP. And what I'm going to do is I'm going to clear our routing table or our session. Basically, it's a route refresh. And what a route refresh will do is allow me to send a new update message so that I can apply policy to it. This is preferred to tearing down the entire session. We're going to do this in both directions. So do show. Okay, so as you can tell, we have the aggregate route in place. We are originating it. That's why we have the quad zeros. And as you can tell, we have no additional AS, autonomous system number path. Let's take a look. Let's take a look at router 1 and see what router 1 is learning. So router 1 is learning the 172.16, which is going to be a /16 network. It's also learning about the 172.16.0/15. This is the aggregate route, and it's also learning about the 17. Let's take a look and see what router 2 is learning about. Okay, same thing. He has the aggregate route with the more specific routes. So let's take a look, and just to get a baseline, if router 4 is learning them as well. And then what we'll do is we'll cut back and leak only what we want router 4 to see. So in that case, router 4 is learning about the more specific /16 prefix from router 2. But what I'm not seeing, which is interesting, let me see something, is this. Okay, that's what I was wondering. Show IP into. Let's do it this way. I think I forgot to turn up the interface. And here we are. Okay, that explains it. I kind of thought that didn't look right. I'll show you guys what I mean with that in a second. Okay, BFD's up, neighbors up. Okay, good. Show BGP IPv4 unicast. And this looks a lot better. Okay, so this is what I was referring to. If we look at the table before, we were only learning the prefixes from one neighbor. So something happened to neighbor 1, and that was the interface was shut down. I didn't turn it back up. Now we're learning about the 172 prefix, 172.16.0 from both router 1 and router 2. We happen to choose router 2 as the best hop, and that's probably because it's the oldest route. And for the aggregate, we're choosing also router 2. Well, actually, it's right here. We're choosing router 2 as the best next hop, and the same with the 17. Okay. So now what we want to do is we want to influence our path selection based on the longer prefix, meaning the more specific route. So the first thing we have to do is I'm going to go back up and add a statement to our aggregation. And that is only to send the summary, basically only the aggregate route. All right, and I'm going to run this just to kind of clear it. We'll do this on all of them just to make sure they all request new update messages. And let's take a look at the BGP table again. And what you'll notice is we only have the /15, but nothing more specific. And we're learning it from both 1 and 2, and we're choosing the path through router 2 as the best. Okay. And if we go to router 1, it looks like he also has no more specific routes. He only has the aggregate. Okay. So now what we want to do is we want to leak the more specific prefix, because we want to now influence the way router 4 chooses how to get to these specific networks. And the way we're going to do this, we're going to do this on router 3, is we're going to create a route map, which is going to match on the prefixes, and then we're going to attach it to the neighbor to tell the BGP process which the more specific routes, meaning the longer prefix, the /16s, get leaked out. So the way we're going to do this is, let's take a look here, show route map. Oops. Show route map. And we do have a few set up. So we have the unsuppressed map, which we can use. And we also have community. So I'm going to show you both. Let me take a look, see what prefix we have enabled. And we are matching on a prefix. Again, if you don't know what a prefix list is, if you don't know what a route map is, that's a whole entire different session. The best I can tell you, prefix matches on the prefix itself, meaning the network portion of an IP address, and we can also match on the subnet mask or the prefix length. And a route map, as I'll show you as we go forward in different examples, is going to allow us to influence routing on the actual router itself. And we use that many times when it comes to BGP on changing attributes, manipulating these attributes so that we can have the particular traffic flow that we're looking for. So in this case, I am interested in the route map I already created, which is route map US underscore, which is unsuppressed map network. And basically what we're doing is we're matching the prefix list, which is going to be this permit network 172.16/16. And if it matches, we're actually not doing anything. We're just permitting it. Okay. So that's a good thing, because that's all we want to do. We don't want to change anything. So as we said on the top, we want the /16 of the 172.16 and the actual aggregate. So let's go into our configuration. I am going to copy this. And what we have to do is we have to apply the route map into the direction of the neighbor that you want this to apply. So in our case, we're applying it towards router 1, and we're doing so in the outbound direction. So that's what we're going to do first. We're going to send a BGP refresh. And let's do this, 192, actually it's, what do we say, 101.1 soft. And let's see if there's any change in our routing table yet. So it withdrew. Okay, let's clear it from this side too. And let's see if we see our route. Okay. So aggregate, and towards neighbor 1, we're sending a route map. Ah, you see, I made the mistake. What I was looking for is this, the unsuppressed map. And now we'll add the route map to it. And it also goes one direction. Let's do a clear one more time. And here we are. So now we have the more specific route that was leaked to router 1, and we still have the aggregate. So what we should see on router 4 now is that we're learning the more specific route through the top link, and we're still learning the aggregate route of /15, but it's being preferred through router 2. Okay, and we'll fix that. I'll show you guys how to fix it in a second, but this is the first thing we wanted to accomplish, that we're actually advertising, we're leaking the more specific route, meaning that if the bottom link does not have the /16, but only the aggregate, that router 4 would always prefer the top link because we're advertising a closer prefix or a longer match to the actual network, which is going to be /16 compared to the /15. So let us now do the same thing, but we're going to do it for router 2 because there we want to advertise this 172.17 network. So in that case, we're simply going to change this unsuppressed map. Okay, so just so you guys see, we're just matching on the /16 of this network. We're not setting any policy. Let's take a look if this BGP table changes. And so far, nothing. So let's give it a second. And we're going to request a route refresh. All right, there we go. And here's the more specific route. It is in routers 2 routing table, and router 2 is going to advertise that onto router 4. We can even check it on here if we do a neighbor to 192.2.4.4, and let's take a look at the advertised routes. We'll also see here we're advertising the aggregate. We're setting the next hop to 3.3.3.3, and look at this. We're also now advertising the more specific route, which means when we go on router 4, we should see the 172.17.0.0 network in here. So let's take a look. And here we go. And here's the network. So this is what we call traffic leaking. We're leaking the more specific route while still having the aggregate route. Now, why would you might want to do this? Well, imagine it this way. What if we lose the more specific route on the top link? Let's just say something happened, maybe somebody was just suppressed the route on the top link. But the actual network is still accessible as long as you get to the autonomous system 64,523. If that was the case, if that more specific route went away, we still have our aggregate route available. They can get traffic from that top link into the proper autonomous system. And then within the autonomous system, hopefully either we have a more specific route or we have a default route, something that will get us to the router that actually can route us to the network. So, but our job is still not done here. And I'm going to show you why. If we do a show IP route BGP, we'll notice that we have the aggregate route. It is preferred through router 2. Yes, and I'm going to touch on the backup route there in a second. This is again, this comes to the quirk with BGP where it only will select one single best route. So we have to do a little bit of an adjustment since we're just peering to a single router when it comes to our cloud environment, which is router 4, but we have 2 upstream links to different routers in the same autonomous system. So in this case, though, the aggregate route, we said we actually wanted to have on both links, so that works, but we're only using it through the path through router 2. Now, the more specific route, the 172.16.0.0/16 network, we are going the right way, and that is over to router 1. So that's what we wanted. And then for the 172.17 network, we're also going over to router 2. Now, Eugene mentioned something interesting here. And that is when you take a look at it, I have a B here. Now, this B means backup path. So if I was to look into my routing table, you'll notice something interesting. If I look at the aggregate route, it will still agree and say the best path is through 192.2.4.2, which is router 2 transit link. But notice this. It says we have a pre-calculated repair path in our routing table towards router 1. So that means if router's 2 path was to be lost, that we can immediately switch to our backup path. So that is one way that we can have BGP actually have 2 paths inserted into the routing table. Now, if we wanted to make an additional adjustment, and again, this is a BGP specific thing. If we wanted to actually have the route show up under this particular routing table, meaning that we're doing something like an equal cost multipathing, which if we're going to do a Ceph lookup right now, is only happening via one link. We can do the same if, let's see, can I do this? Okay, and here the aggregate route goes to router 2. So if we want to influence that, we have to do a little bit more finooning, as they say. So do show run BGP. I'm going to go into the process. And the first thing I'm going to do is I'm going to remove this. Okay, and then just to take a look at it, we still have it in here. Let's do a do clear BGP IPv4 unicast star soft. And as you know, and as you can tell, the B's are gone. Now the problem with that is, as you see, for the 16, we only have one path through router 1. For our aggregate, we do have 2 paths, but we're only choosing one through router 2. Okay, so we want to influence that. The way we do this, we go on router 4, and we use this command, the maximum paths command. And in this case, we want to influence iBGP, and we're going to give it 2 paths. Now, you're going to notice an interesting message pop up. It tells us this may cause traffic loop if not used properly. And once again, this may cause a traffic loop. So while we can do this to provide some type of multipathing, it is not the optimal solution because of potential loops that are introduced. That's why we want to do the repair path. But we'll notice this now. There's going to be an M next to the actual aggregate route. And if we look at the legend, M means multipathing, which is also part of the BGP best path selection algorithm. So what this allows us now is to use both paths at the same time. And to prove it, let's take a look at our routing table. And here you go. We're learning the aggregate via router 2 and router 1, and we can use both paths. Let's prove it. Let's do a do show IPsef, and let's do 172.16. Well, actually, we'll have to do this 16. And take a look. Now we're using both paths towards it. Yeah, so the FIB, so IPsef is the forward information base. That's basically where we're doing the pre-calculation on what's going to be our next hop IP address, what's going to be our upcoming interface. And then on the back end too, we're going to do already the calculation for our layer 2 header, source and destination address. Again, it's a little bit outside of this workshop, so I won't go into more details, but I'm looking at the show IPsef because I want to know from a load sharing and a load balancing, and including what the algorithm of Cisco Express forwarding will do based on how it's going to forward the traffic. So that's what interests me. Because otherwise, sometimes if you notice, it doesn't always show in the IP route RIP table on what possibly Ceph can do. This is one of those things, especially, let's say, if you don't have a more specific route in your routing table, but then you do an actual lookup in your CIF, in your FIP, basically your forward information base, you'll notice that that particular prefix or that particular network that you're trying to reach could be, let's say, reached via default route. That may not always be obvious when you do a specific lookup. So in either case, as you can tell, we accomplished our goal in using both the top and the bottom link, link 1 and 2, to route our aggregate route. We prefer the more specific route through router 1 for the network 172.16.0.0/16. And for the bottom link, for the second link, we prefer router 2. So, and as a little bonus, no, listen, Eugene, it's fantastic. Keep up the feedback. Feel free to give your 2 cents. What I do want to show you also is, if we look at one of the more specific, look at the aggregate route, you'll notice something as well here. And this is, we have a new attribute. That is the atomic aggregate. This is a well-known but discretionary attribute. So as you can tell, this is new in there. It gets populated in there. And also, we'll notice that when we look at the best path selection, let's do it this way. That it chooses the top link because it's younger. So it goes through all the BGP best path selection process, meaning it went through weight, local preference. It looked at the, well, actually, let's walk through it together. That might be a good exercise, right? So we're going to look at the weight. We have no weight configured. We don't see any weight. Next would be our local preference, which we see is 100 and 100. The next thing that we're going to look at, if you want to remember, we love oranges as oranges mean pure refreshment, is going to be our locally originated route. This is not a locally originated route. We can tell because it says external. And if we really want to get granular, we know that the next hop is different. So we're not the actual originator of this route. Next, we want to look at the length of the AS path. The shorter the AS path is, meaning the less autonomous system numbers in this path, that's the one we prefer. In this case, it seems like our autonomous system path is only 1. So that's a tie, that's a wash, and we'll move on to the next attribute, which is going to be our metric or our med. So in this case, we don't see it actually listed here, the metric, which means that it's going to be 0 in iOS. And it's going to be a wash. We're not going to consider it. Next, we're going to look at, is it an external route or an internal, basically eBGP over iBGP. So in this case, both routes are external. So that's a tie as well. So we can't make an actual decision on installing this as the best path yet. Then we would normally move on to the shortest IGP distance, but we don't have anything injected through iBGP here, so we don't see the metric associated with that. So the next thing we get to, what is the oldest path? So in this case, we're lucky we have the iOS XE telling us when the route came in. This one came in at 2216, and this one came in at 2215, thus making it the younger path. And as you can tell, the best path is number 2 because it is the older path. So again, we're talking about stability within the BGP RIB, and as well as our IP routing table, which is going to be our actual global routing information base. Okay. Do you all have any questions in regards to this first part before I show you an alternative to making this work? Okay, if you do not, let's do this. Let's reset what we did to baseline. And then I'm going to show you a quick another way. And we're going to use a different attribute for that. We're going to use communities. So before I get into that, let's go ahead. Let's remove this. So in that case, we want to remove the unsuppressed map. Okay. Let's do this on all the routers. Okay. So before we had 2 paths. Let's take a look at what we have now. Okay. And it looks like right now all we have is the summary route. So let's see why that is. We're still multipathing, which is good. And we're not receiving more specifics, which means that neither router 1 and router 2 should also receive the more specifics. Okay, so let us do this now. On router 3, we had a route map, which instead of simply leaking the more specific route, we want to attach a community attribute, which is going to tell routers 1 and 2 that we don't want them to export this particular route. And then we'll take a look at what also that looks like on an actual packet capture, and as well as on the actual command line. So in this case, what we want to do is we want to set this route map to the neighbor, just as we've done before. So we're going to do neighbor 1.1.1, and we're simply going to apply route map. And we're going to apply in the outbound direction. And we're going to do the same thing for our next neighbor. But in this case, we call the route map community export. We're going to do outbound direction. And let me do one thing too, because we don't want to make sure that this actually is right here. Okay. Let's clear requesting a new BGP update message. Okay. So where is our, let's take a look. Make sure I did not completely delete our summary. Okay, there it is. All right, let's see if it just took a little bit to get here. Okay, so we have the more specific route, the 172.16.0.0/16. We got the aggregate for that, and as well as the more specific for the 172.17. Let's take a look briefly at router 4. And let's see what it is learning. Okay, so in this case, router 4 says to get to the more specific prefix of 172.16.0.0, I'm going to use my link to router 1. So it's going to go through this link. When it comes to the next specific route, which is 172.17.0.0, I'm going to go through router 2. So it's going to go down this link. If I'm trying to use the less specific route, which is going to be my aggregate route or my summary route, Since I have multipathing enabled, I'm going to use both. So let's take a look at our routing table and take a look at what we're doing here. So when it comes to the 172.16/50 network, and here's the proof in the pudding, we're using both routes, basically from router 4 to router 1, from router 4 to router 2. On the top link, we're preferring to use router 1's connection to get to the most specific prefix of 172.16.0/16. And then, as before, also the 172.17 network on the bottom link. So let me take a look and see if, I don't know how far I'll have to scroll up to see this. We'll do this, and let's take a look. Okay, path is empty. So it wasn't in here. Let's take a look here. And what I'm specifically looking for is to include this attribute. So I'm hoping I caught it. Keep alive. All right, let's make sure that this was actually received the way we configured it on routers 1 and 2. So what we're looking for is the 172. Let's take a look at this route first. Okay. All right, so it's a 17. So this is specifically why we don't see this happening. I should have actually, where is, actually, this is the right link. That's interesting. All right, let's see if we can figure this out in a second. What I want to show you is we set on the top link, which is this link, we did not want to advertise the 172.17.0 network. So this is what we said. We did not want to advertise that on top. Notice now a difference from before. We have a community attributes. And the way you want to think of communities is that it basically just is a tag that we can attach to a route itself that can possibly either signal the local router to perform an action when it matches, let's say, a policy, or since it's a transitive attribute, it is optional, but it is transitive, that we can impact other routers and other autonomous systems to apply policies based on these tags. So in this case, what we did is we applied from router 3 the no export community, which is a tag that basically tells router 1 that, hey, listen, I don't want you to export this particular route. So in our case, it's 172.17/16 to any other autonomous system, meaning keep it local. I don't want you to send it to anyone else. And we see the result of that in the sense that router 4 only knows about this network from router 2. Again, if we scroll up, we don't even learn an alternate path that we can even match on, maybe do some type of multipathing or make it a repair path, simply because of that particular community tag. Router 2 should have something similar for the 172.16.0 network, where it adds, or it has, the no export community. So in this case, the no export community, just as attributes, it's a well-known community. Mike mentioned it earlier. We generally have a no advertise community, which means do not send beyond the local router. And then the no export means do not send it beyond our autonomous system. And then we have a little bit of an odd one, which is the internet community, which basically kind of is like a permit any and overrides anything else. If we look at a route map, and I'm just going to say fake permit 10. Did I make something? Fake. Yeah, let's do a route map and not show. So if we look at here, let's say we want to set, and just to give you an idea, we'll go into this, but these are a lot of stuff that we can influence on. A lot of the things are BGP related. So what we want to look for is, actually, it's just communities. It's right here. We have our internet community. It will tell you that it's well known. We have a local AS, which means do not send beyond our local autonomous system. It's also well known. And then we have the no advertise, which basically means this does not go beyond the local router. So wherever it's applied, it does not go any further. And then the one we used was the do not export community, which gets not propagated to the next local autonomous system. Again, a community is just another way to perform BGP traffic engineering. And it is either a 32-bit value, if we're talking about a standard community. We can also have an extended community, which is just a larger field that we can use, which is going to be, I believe, 64 bits. And we also have large communities, which are going to be 96 bits. All that means is that we have more bits, more values to influence traffic. Now, communities, like I said, are a scaling solution, very helpful. Let's say if you cannot influence necessarily or don't want to do it manually, let's say your service providers like AT&T, British Telecom, Verizon, they're going to have already a routing policy set up that match on certain community strengths. And when they see you signal with them, they can apply policy to it. It could be local preference. It could be if you want to apply some type of metric to it. Or you can even signal downstream routers to perform certain actions based on these communities. So communities are very, very powerful solutions. Yeah. And let me see if I happen to be able to find. If I can't find it, we'll move on, but I would love to show you with an actual update message. Origin. So that's the problem. Sometimes these things, here we go. This is the one I wanted to show you. So again, we got path attributes. We have the mandatory ones, origin, AS path, and next hop. Our optional and non-transitive is the multi-exit discriminator. Our well-known but discretionary is going to be our local preference. And then our optional transitive is going to be our communities. And as you can see, there really is not much to it, but that's the actual hex string that is associated with the no export community. So you'll see that it's a different type code compared to something like a local preference. And it will tell you that it's optional, it is transitive. So that means it may not be necessarily supported by you. And if it's not, just keep passing it on until it gets to its destination. So, and just to give you an idea, I still like the prefix and the unsuppressed map. But for example, when Mike and I spoke, Mike really liked the community signaling because of its power. And you can also do custom communities to do any type of other signal. When we look at other solutions such as MPS layer 3 VPNs, that's where we're going to use the community, especially extended communities, to signal our route targets and route distinguishers so that we can make sure that we're importing and exporting our routes in the correct routing table. But again, a little bit beyond our current predicament. So let's take a look here. Oh, actually, what I'm going to do.
Yeah, Mark, I use BGP communities everywhere because it's super easy for me to set a community, match a community, and take an action upon a community.
Yeah, it's really, because here's the problem that you can get. And this is where you want to keep in mind. If you want to quickly put me and Mike back on the screen, we can briefly discuss this. It is paramount to know what our options are when it comes to which attributes we're going to influence. So in this case, all we did is some traffic leaking right now, and we used a particular attribute to either allow this particular router to export it to our next system. Now, there could be instances, let's say that we want to influence the way traffic, and we'll do this through AS prepending, how traffic comes back into our autonomous system. But here's the thing with BGP. You have full control of your system because it's under your control. You can hope whatever you're trying to impact on the outside so that traffic returns a certain way, that it will be honored. But, and I know Mike knows this, so this is not a weird question. But if I'm influencing my path through AS prepend, through the AS path length, how could you easily negate that? If we're thinking about the weight, the local preference, the AS path, and so forth.
Yeah, you could just change the weight, and automatically you negated the local preference. Yep. The other thing is somebody else could send you a different local preference if you chose to. So yep. It's really about knowing what we're getting, where we're getting it, and architecting it in a manner that we have everything pre-planned ahead of time. So when those network engineers build it out, we've already thought about every possible impact that's going to occur along the way. As you can see why I like architecture. I design it, I present it, I go sell it to somebody else, and then somebody builds it. And this stuff, building this stuff, this gets hard. And when you have to come in at 3 o'clock in the morning to build it, and you're tripping, and you get called at 3 o'clock in the morning, there's a network outage. Mark and I were just talking about it the other day. You trip, you stub your toe because you can't see anything. And then you drop your coffee cup on the ground and you're trying to drink your coffee on the way to the office. It's just, it's a harder job. They're all great. And I love networking. I love network engineers. I've been a network engineer. But you can see the complexity of building it versus designing it, and why we need people with different focuses, hopefully.
Yeah. And for example, you will need to know how to actually configure this, right? Maybe Eugene, myself, Mike, we might be a little bit more geeking out. We'll enjoy it. We'll like to break it, see what it does. But from an architect perspective, knowing that you have the option of using something like a community attribute to influence other routers downstream of you or upstream, depending how you want to view it, that's where the architect focus come in. You want to know that you have the option to do something in BGP. You're not the one going to sit there and do it like what I'm doing right now, but you want to know about the options. You want to know how something functions so that you can adjust it. Because the beauty about BGP is it is a policy enforcement protocol. That's really what it does. You can do it network-wide. You can try to influence other ones. But the other reason why BGP is so great, it can mirror business requirements. For example, what if I have 2 links? So if the 2 links I have, let's say one of them I paid more for than the other one, or one is more expensive than the other one, or I have more bandwidth on one over the other one. So now it becomes a business decision, which link I want to utilize more. In this case, it might not be best that I send routes equally. Basically, I do load sharing across both routes because it's going to cost me more on one side compared to the other one. That's perhaps something you can do. This is quite prevalent when you think of something like a service provider. If they're actually having a peering to another service provider, one of the peering sessions could perhaps be settlement free. It costs nothing. This could be based on because one is larger, they're the same size, maybe one is smaller. Maybe the traffic that they're sending each other could be the same. So it kind of is a wash when it comes to the expenses. But then on the other side, what if you, and this is one of these big issues in net neutrality, if you think about what with Netflix and the FCC and ISP, where they make the case, well, Netflix is sending us a lot of traffic. they should pay us extra. So those ISP consider this peering relationship between them and Netflix to cost money. So this is where we have to keep in mind, this is where we can influence paths.
Yes.
So Netflix can do whatever they want to on their side, even with communities. What if the ISP decides, you know what? I have a Cisco route, I'll set my weight. You can't override it. What if they said, you know what, instead of just being locally important, I'll set the local preference, which is going to be propagated through my entire autonomous system.
Yes.
You can't override that.
Nope.
There's nothing you can do on your end that can influence that decision-making locally to the service provider. And that's why you need to know about the actual attributes, how they work, which direction they're being applied to, and why you're doing that.
And actually, that goes back to the topic someone asked about, how can I build a lab to learn these? You can't learn this in the lab. I wish you could. The lab teaches you how to. This is understanding how something works. It's understanding the why. Why do I want to AS path prepend? Why do I want to leak a more specific route? What's going on at this peering point where I want to influence my traffic in a certain direction? Why do I want to use one link over another link? Why do I want to aggregate my routes? What happens if I have too many routes on my routing table? What do I want my IBGP environment to look like? Do I use route reflectors? If I use route reflectors, what do I lose versus what do I gain? If I use confederations, what do I gain? Do I use a combination of route reflectors plus confederations to kind of keep them? And all these things that you need to think about, this all goes into the architecture, which is all about the why, not the how to.
Yep. So again, you may not need to know every single attribute by heart. That's why you have documentation. For an exam, might be important, but otherwise just know that you have the tools available. Okay. So with that, Chris, if you wouldn't mind, I'm going to move on to the next attribute because we want to do some additional traffic engineering. That's what Mike and I showed up for, and I know the rest of us too, just to see how we can influence the path. So if you would go ahead and share my screen again. Okay. So the next thing we're going to try to accomplish is on, and let's see, where's my pen? Here we go. On link number 1, for the 172.16 network, we want to set the weight, I'm just going to do W if you guys don't mind, to 35,000. That's going to be on top link. And for the 172.17, we're going to set the weight to 32,768. Okay, so this is higher, and higher is preferred. So again, this is link 1 and link 2. Next, on link number 2, for the 172.16.0 prefix, we want to set the weight to 32,768, but for the 172.17.0 network, we want to set the weight to 35,000 even. Okay, so basically we want to make sure that we always prefer the top link for the 172.16 network, and for the second link, the bottom link, the 172.17 network. Now, what I've done already in the background, I've removed the aggregate. So if we look at our BGP table here, and I'm just simply advertising the more specific routes, which is going to be the 172.16/16 and the 172.17. And that's also going to be seen on the routing table of routers 1 and 2. So once again, the 172 and the 16, and our next hop is router 3. Let's take a look at router 4, just to make sure that it also is in unison, and it is. In this case, we have multipathing enabled. And let's see. Let's do this. Let's remove multipathing for the time being. Okay, And let's do BGP additional. If I could type, let's see, additional. Let's do this since apparently I can't type. And we're going to install. Okay. And all we want to do is do clear. Okay. So we created the repair paths again. But in our actual local routing table, as you can tell, right now we're preferring router 1 for the top link and router 2 for the bottom link. So just so you guys understand, this just happened to be because of the way the sessions came in and the routes were learned. So we kind of already established what we were trying to do. But in case there's any flap or anything, this might change. We still could have the 172.16 route be eventually preferred over router 2. So this is just the default state. It's probably based on the, actually we can take a look at it. It probably tells us it's younger or something. Let's take a look. Yeah, you see here, it chooses, for example, for this prefix, it looks like the first path through router 2 is younger. We prefer the older path. So if we look at it, this is 2247, 25, and this just came in a couple of milliseconds sooner or seconds sooner. So as you can tell, if we were to actually bounce the connection, that might change. So we want to nail it down and make sure that we're preferring them as it was written. So to be able to accomplish that, again, we have to think about it. Who are we trying to influence? So in our case, we want to make sure that router 4 prefers this link for the 172.16, let's just do /16 network, and the bottom for the 172.17, and then let's do /16. So it is going to be a local decision. And to accomplish that, we're going to use the weight attribute as outlined. So what we'll need to do is let's take a look and see what we even have available. So we have prefix lists that allow us to match the routes that we're receiving. I don't believe we have any route maps. So let's take a look. We don't. Okay. So what we want to do is we want to create route maps so that we can influence our BGP decision. So what we're going to do on router 4, we're going to create a route map, and we're going to name it weight from 1 and actually that's it, and let's say permit 10. Okay. So now looking at our route map, what we want to do is we want to match the prefix list. So I'm going to match this 172.16.16 prefix list. So if I do a match statement, as you can tell, there's a lot of things we can match on. But I specifically want to match on this particular prefix list. Next, I want to set the weight attribute to something different. So if you look at it again, you have quite a few attributes here, including some additional routing protocols that you can match on. But the one we're interested in is the weight attribute. And as you can tell, we have the ability to set it from 0 to 65,535. We said when it comes to the 172.16 network, we want to set our weight to 35,000. Let's do that. Now we need to influence the 172.17 network on the top link, and we want to set the weight lower. So what we're going to do is we're going to add an additional sequence, because just like an access control list, route maps are read from top to bottom. And within this sequence, we want to match, number one, the prefix list associated with the 172.17 network. And we want to set the weight to 32,768. And since we don't want to influence any additional routes that are coming in from router 1, we're going to set up a permit kind of any route map, because otherwise it's going to drop everything else. and we're going to not match anything or set anything, which means it's basically going to allow any other route that we receive in from router 1 to simply pass through without any policy application. Okay, so our route map at this time, let's do this, would look like this. We have a sequence 10 where we're matching an IP prefix list. This prefix list contains the permit statement for the 172.16.0.0/16 network. If it matches it, we want to set our weight to 35,000. Once that is completed, we have an additional sequence which matches now on the next prefix, the 172.17/16. And when that is received, we're going to set the weight to 32,768. And then we have a final sequence that just says allow anything. Okay, so let's take a look. We're going to apply this policy first. And let's take a look at what our local routing table will say. So at this time, if we look at it, we see that right now we don't have any weight really applied, right? Not at least to anything that is not locally originated, which is an iOS default that it will set to 32,768. So let me do this because I do not want to mistype the route map. We're going to go into our router BGP configuration. And now here's the question. Am I applying the policy for weight inbound or outbound? And that's a question for you all. That also shows me that you're still awake, that you understand where we're at. Towards which direction am I going to apply this policy towards? Is it going to be an inbound policy or an outbound policy? Okay, Mohammed says inbound. And you're welcome to guess. Again, I don't necessarily expect everyone to know it, but go ahead and guess if you don't know. You only have two options, so that means you have a 50-50 chance of being correct. Mohammed says inbound. I'll have you think about it this way. We're trying to influence how traffic leaves our autonomous system. So in BGP, if we're trying to influence traffic going out, the policy has to be applied inbound. If we're trying to influence how traffic comes into our autonomous system, the policy is applied outbound, because we want to influence other routers and their decision on how to return traffic to us or just send us traffic in general. So in this case, weight is anyway a local router attribute. So it's not really recognized. So it doesn't get passed. It just stays there. So in that case, what we want to do, number one, we want to apply it though onto the neighbor statement towards router 1 because we're learning the routes from router 1. So in that case, I'm going to add router 1 in here, which is going to be the 192.1.4.1. And what I'm going to do is I'm going to add a route map here. And now it says, do you want to apply it inbound or outbound? I want to apply it inbound because I'm learning the prefixes from router 1. As I'm learning it, it goes into my adjacency in RIP, my BGP adjacency in RIP. I'm going to take whatever in there, and as I move it towards my BGP RIP, I'm going to apply policy. And then depending on what the policies that are applied, if it's a valid path, if I can access the next hop, Then I will install it into my routing table. So let's take a look and see what our BGP table looks like, our routing table. So it looks like right here for the 172.16 network, when it is learned from router 1, look at this, we're applying the weight of 35,000. Alternatively, for the 172.17 network, right now we're preferring it through router 1 because our local weight metric is set to 32,768. As you notice, if the weight is not set on an externally learned route, it's always 0. And what we said is higher is better. Thus, because router 2 does not have the same policy applied, no weight is applied. So everything right now is going through router 1. So let's change that up. Let's go back and let's create an additional route map. And I'm going to cheat a little bit. So what I'm going to do is I'm going to take the route map that we have here. And what I'm going to do is I'm going to simply change it to 2. And I'm going to match. It's going to be the same thing. I'm going to match on the same IP prefix list. But instead of setting the weight to 35,000, as I did in this example, for the bottom link, we want to set the weight for the 172.16 network to 32,768. So I'm going to do that. And then I'm going to move on. I'm going to create our next sequence. Here, I'm going to match the 172.17 network, but I want to set the weight to 35,000. And then, of course, to round it up, because we don't want to apply or deny any other prefixes, we need an empty route map sequence, and we should be good to go. So let's take a look at this route map, just quickly run through it, what we did. So we're going to do show route map from router 2. Again, we're matching the prefix list 172.16/16. If it matches, we're going to apply the weight of 32,768. If the next prefix and sequence get matched, which is for the 172.17 network, we're going to apply the weight of 35,000. So that is in unison with what we agreed here. Okay. So now what we want to do is we want to apply the same policy as we had before from routes being learned from router 1. Now we want to do it towards router 2. And let's do this. We're just going to copy this, make some minor changes. I'm going to give it a moment. And right now, I'm still, as you can tell, nothing has changed. This is still the old routing table. So I'm going to see if I can refresh incoming update messages. So I'm going to do a soft in. And let's take a look at our routing table or our BGP table again and see if there's a difference. So there definitely is. So let's start off with the 172.16 network. So in this case, per our design, we're not preferring router 2 as our primary path for the 172.16 network. We're preferring router 1. And again, this is shown by the greater than sign under this particular prefix. Now, alternatively, as we've just done with the route map, for the 172 prefix, we did not want to prefer router 1, but router 2. And the way we have done that, we set the weight to something lower than 35,000. And then, of course, since it's set to 35,000, we're preferring router 2. Now, this is what I want to show you guys, though. If I go, let's say, to router 5, and if you recall, router 5, we have the BGP session set up, but notice this. He has no weight set. So again, router 5 does not have the weight set. So router 4 never sent it to router 5. Now let's take a look at router 1. Again, router 1 does not have weight set. So this proves to us that weight is not a transitive attribute. It is locally significant only to the router on which we configure it. So that's how we influence path selection when it comes to the weight attribute. Does anyone have any questions about the weight attribute before we move on? And we're going to look at something that is a well-known but discretionary attribute through local preference and how we can influence the exit that we want to take out of our autonomous system. And while I wait for your questions, if you have any or you need clarifications, I'm going to reset this configuration so that we can move on to the next attribute. And Chris and Mike, if you guys want to let me know if there's any questions in case I miss them as I'm clearing this out, I would appreciate it.
I haven't noticed any new questions coming in.
All right. So either I'm doing an excellent job. No, go ahead, Mike.
But I was saying the only thing that I noticed was Mark was talking about his buffer overflow. But I know Mark, and I'm thinking he's joking about that. He's a super technical guy.
I must have missed that one. A buffer overflow has occurred. No, thankfully it hasn't on this side. I'm sorry if it has on yours. But in either case, let's take a look here. We've removed. Oh, Mike, anything you'd like to add before I move on to local preference?
No, I think you're good. So, you know, Mohammed talked about which other vendors actually support weight. You know, I knew it as Cisco proprietary, and it always was until fairly recently. I do know that AWS does support weight. Does Arista support weight? Because Arista came from all Cisco people that went over to Arista, so they may have actually done weight right now. I'm not sure.
Don't know the top of my head, to be honest. It's very similar also to as you go from one vendor to another. For example, Juniper, they will support. They have a little bit different of a best path selection algorithm that go through it. I know, for example, they consider accumulated interior gateway protocol metrics. That's something you don't see default being viewed on Cisco routers, for example. They, for example, also will not use, weight. So I would suggest that depending on which vendor you eventually work with, it's going to be different. Go ahead and check, right? Because again, remember, these attributes are going to be supported and not supported. So you want to know exactly which ones and which ones are not.
Yeah, and all these implementations and all these routers, they have these well-known mandatory type things that they have to support. And then they have their own enhancements. So in a multi-vendor environment, we have to go with as close to possible as an industry standard. Because when we don't, that's when things break.
And I'm going to do one thing I forgot earlier when I was talking about communities. But the reason we were talking about communities is as a cloud architect, you want to keep in mind that you can signal certain actions to the AWS environment through communities. So what I'm going to do is I'm going to pop that in the chat so everybody has it. It is not something that I can actually demonstrate, but just as a reference, AWS does post it, what these tags are, basically the backend policy for these tags and how they're going to interpret it. And you'll notice there's some very known ones when it comes to the no export BGP community. There's also going to be some in regards to your local preference. So if you have the time, bookmark that, kind of go through it a little bit in case you ever have to deal with that, at least that you know from a high level overview that this is actually a possibility. So figured I mentioned that before I forget it again. Okay. Aside from that, I don't see any additional questions. So what I'll do is I'll move on to our next attribute, the local preference. And what I'm going to do in this case, unless I see anyone ask any specific questions, because I don't want to keep anyone much longer than already, what I'll do is I'll pause once I'm done, meaning we'll go through local preference, we'll go through AS path prepending, and then we'll go through the multi-exit discriminator. And then we'll come back and we'll answer any questions if they're there. Okay. All right, Chris, if you wouldn't mind, if you can get me back to the screen share. Okay. So what I've done already is I've reset our BGP configuration. So as you can tell, the routes are zeroed out when it comes to our weight, meaning this is back to just choosing most likely based on which path is younger, which path is not. So what we're going to attempt to accomplish now is on link number 1, for the 172.16 network, we want to set our local preference. I'm going to abbreviate just as LP. We want to send that as 200 on the top link for this particular prefix. And for the 172.17 network, for the top link, we want to send our local preference to 100. For link number 2, which is going to be our bottom link between routers 4 and 2, for the 172.16 network, our local preference, we're going to set to a 100. And for the 172/17 network, we're going to set our preference to 200. So basically the inverse. So to do that, it's going to be the same thing. We're going to apply, or we're going to create a route map. The route map is going to reference our prefix list so that we know what prefix we're going to apply to. We can also, at other occasions, we can even apply to an autonomous system path. So basically, any type of route coming in from this AS path, or perhaps it had the AS path in its AS path list. We're not going to demonstrate that, but again, it's a possibility. In this case, we're just going to focus on a particular prefix that we're receiving from router 1 and router 2. So as previously, we only have the prefix list available, which for the first entry, it matches the 172.16 network, and then for the second entry, it matches the 172.17. We don't have any additional route maps. So what we're going to do, again, local prefix, we're going to apply it inbound, because what are we trying to influence? We're trying to influence how traffic leaves our autonomous system. That's what we're trying to impact. So again, we're trying to impact an outgoing traffic, which means the policy needs to be applied inbound. So let's take a look here how we're going to accomplish this by creating a route map. So we're going to create a route map, and we're going to call it local preference for short. And we're going to say from, well, we just do to R1, and we're going to do a permit 10. Within this route map, we want to match the prefix list for our 172.16 network. And then what we want to do, and this when we look further down, you'll notice we have the local preference option. So we want to change the local preference. And in this case, pick your poison. You don't have to go ridiculously high. In this case, we'll just go for 200. And since we have done that, we are going to create a different sequence. And in here, what we want to do is we want to match the IP prefix. Actually, let's do this. There we go. And we're going to set the local preference to 100. And do not forget, there's an explicit deny at every end of a route map, just like an access list. So we want to create just an empty sequence that matches anything but applies no policy, which means it just gets passed through the actual route map. So let's do a show route map just to kind of see what we have. All right. It looks like we're matching on the proper network address. we're setting it for that network to a local preference of 200 for the 172.16 network, and for the 172, and as you can tell, I've made a mistake in how I typed it here. So we'll have to correct that. So what I'm going to do is I'm going to go in here and let me get rid of the match statement right. Actually, the sequence 20. Now let's remove this because I made a typo, right? So what we want to do here actually is that. Okay, let's take a look. Okay, so that looks better. We're setting the local preference to 100. Okay, so instead of applying it, what I'm going to do is I'm going to create the secondary route map that we'll need from router 4 to router 2 as well. So in that case, we'll cut and paste certain things. So in this case, we'll change this to router 2. We're going to match the top prefix as well, the 172.16 network. Here we agreed upon, we're going to set this to local preference 100. Then we're going to create another sequence. In here, we're going to match the 172.17 network, but we're going to set the local preference to 200. And then finally, we're going to create an empty sequence in our route map just to pass any other type of traffic through. So do show route map just to make sure that we have things in place. There's no typos. All right. And now what we're going to do is we're going to apply it to the neighbor in the incoming direction. And then we're going to take a look at seeing what does our local preference look like. So at this stage, we have no local preference configured, as you can tell, besides the one that was sent from router 5 to us. So let me do this. Let me copy at least one of them. Okay. Let's go into our BGP process. We're going to go under our address family, IPv4, and we want to apply as routes come in from router 1. And we're going to apply the route map in the inbound direction. So that's where we're going to start off first. We're going to request a route refresh coming in so that we can apply our policies without resetting the actual BGP neighborship. And now let's take a look and see if our local preference was applied. Okay. So as you can tell, there's already a difference here. We're at least seeing a 200 listed and another 100. And as we mentioned before, a higher local preference is preferred compared to a lower local preference. So in this case, when it comes to the 172/16 network, the link number 1, that means from router 4 to router 1, is preferred because of the higher local preference. And because of the lower local preference, right now we're not preferring router 2 or router 1 to get to that 172.17. And again, generally speaking, the local preference is 100, so it's a little bit of a wash. So let us now apply from router 4 to router 2 the actual policy. So let's go up. Let's clear our, well, let's request a route refresh. And let's take a look at our routing table again. Okay. So let's run through this again. For the 172.16 network, our initial intent was to prefer the top link. So what we ended up doing is we assigned a local preference of 200. We preferred the bottom link for the 172.17 network. And what we did is we set the local preference to 200. Just to verify it, let's take a look if BGP also agrees with us. When we look at the actual prefix itself, And as you notice, we got inaccessible here, so that's not what we're looking for. What we're looking for is up here where it says we have 4 available paths. It tells us best path is number 3. So this is 1, this is 2, and this is the best path. It tells us it's overall the best path. And considering the other paths we can't use, notice what it tells us. This is not selected as a best path because of the lower local preference. Okay, let us look at our routing table. And let's see if that holds true. So for the 172.16 network, we prefer the top link. For the 172 network, we prefer this link. Now, here's going to be the interesting part. When we look at the routing table on router 5, let's see if there's any change in anything. Okay, so if you pay attention, notice here, the local preference on router 5, we didn't make any configurations, we did nothing. We simply configured router 4. It actually sent the local preference value to router 5. So router 5 now will prefer the top link, meaning towards router 1 for the 172.16 network, and will prefer the link through router 2 for the 172.17 network. Now, router 5 only has one egress point anyway towards router 4, but this is to show you all that if you want to influence the exit decision in your autonomous system and you want it to propagate to all BGP speakers within an autonomous system, you would have to use the local preference attribute, not the weight attribute. Okay, so simply said, we can see what happens here if we do a trace route. And what we're going to do, just for demonstration purposes, let me see what the actual IP address is. All right, let's pick this one here, which is going to be for the 172.16 network. We're going to source our local loopback address. And let's see what path it takes. All right, so it goes over to router 4. From router 4, it takes the link, the top link between routers 4 and 1, and then it goes through the transit link from router 1 to router 3. Let's take a look what happens when we try to go to the 17 network. See if there's a change. Okay. So our first hop is going to be the 10.4.5.4, which is going to be router 4. Notice this. It now uses the link between router 4 and router 2, so the bottom link. And then the link between router 2 and router 3, as demonstrated here. And this is due to the local preference that propagated to router 5, and of course is in effect on router 4. So that's how we use the local preference attribute. You're welcome to type in any questions you have about it. What I'm going to do in the meantime, I'm going to clear our configuration. And let's do this. Are they all in the same? Yeah. Let's just do a quick one like this. Okay. Let's send a refresh signal to all of them. And let's take a look here. Again, as you can tell, local preference has been reset. All right. The next attribute that we want to deal with is going to be our AS path. So in this case, what we wanted to accomplish is the following. Let's see where my pen is. Okay. So for link, here's link 1 and link 2. for link 1, what we're trying to do is for the 172.16 network, we want to set our AS path. I'm just going to do AS to only have at least one autonomous system in its path. So it's going to be the shorter. So it's going to look something like this. For the 172.17 network, what we want to do is we want to artificially increase our AS path. Thus, what we're going to do is we're going to add an additional instance of our own autonomous system onto this actual AS path, thus making it longer. So that would be what we're trying to accomplish on the top link. And then, of course, to make sure that since we are, in a sense, dual home from routers 4 to router 1 and router 2, we have to do the same thing also on the opposite side. So in regards to this network, on the bottom link, we're going to increase our AS path, at least to something greater than we're going to do for the other network. And on the bottom, we'll make sure that it's going to be shorter. So as demonstrated earlier, now the question really is going to come, and this is the interesting part. We have made the configurations originally all on router 4. But now you have to ask yourself, who is the originator of the prefix? Now, in our case, it is router 3. He actually owns the networks, which means whatever policy we apply, we want to apply it in the outgoing direction so that we can influence incoming traffic. Since these two networks live within the autonomous system 64,523, which is our data center, we're going to apply the route maps to routers 1 and router 2 so that we can influence the way routers 5 and 4 will enter our autonomous system based on the AS path length. So let us go to router 1 and let's take a look. I believe we should have a prefix list on here. We do. Fantastic. So let us go ahead and configure a route map again. And what we're going to call this route map is AF, let's do path prepend from, this is R1. So what we'll do is R1 to R4. And we'll say permit 10. Now what we're going to do is we want to match, of course, the prefixes. So we're going to start off with this one. Okay. And then we take a look at our options. We want to influence the AS path. So as we look at it, it will ask us, do you want to prepend it? Yes, we do. And then ask us, what do you want to type? You want to last? Whatever. We're just going to say, in our case, we want to prefer the top. So actually, we can do it this other way. We don't even have to do this part, but I'll show it to you guys. Actually, let's do it this way. Let's do it this way. Let me just take a look. Okay. So the only thing I changed is it's already, the AS path is only anyway one AS path. So what we're going to do is we're going to lengthen the 172.17 on the top link. So we only need one statement, but it's going to be the same thing. We're going to go in here and we're going to set the AS path prepend. And what we're going to do is again, you want to prepend your own autonomous system number. Do not prepend other people's autonomous system. That's bad practice and that's malicious. So again, only your own AS number. So in our case, it's 64,523. We're going to append it twice, which means we'll have an AS path of 3. And then just to round it up, because we want to make sure that we're allowing other traffic, we're going to create a final route map, and that is it. So do show run, or we can just do a route map. This is going to be our route map. So I'm going to copy this, And I'm going to apply it towards router 4 in the outgoing direction because I want to influence incoming traffic. So let's go to router 4. We're going to say 192.1.4.4, and I'm going to do it outbound. So as you can see, right now, I only have a single AS path, so nothing has changed. So what I want to do in this case, let us see if we can even capture it maybe. Scroll down in case it comes through. And what I want to do is I'm going to request, I'm going to do from router 4 a refresh in. And let's see if we can see it happen on this link. It was actually here, right? So here's our route refresh. What we see, let's take a look what we have included. See if this is the proper message. I don't think it is. Let's go to the next one. And here we are. So if you take a look at this right now, the autonomous system path is 64501, 64523, and we should, if this is the right message, it may not be, see it, but let's take a look at router 4 already. And here is the difference. So something did not match correctly. 1 second, what didn't match here? Oh, and that is what, if I would have done this command, I would have noticed this. I applied it, instead of a prefix list, I applied it as an access list. So let's make that quick correction. So let's open up our route map. I'm going to say a no to this particular match statement. And all I'm going to do is I'm going to copy this. Well, actually, I'm going to copy this only. I'm going to say match IP address prefix. And here we go. So that should be correct. So let's do a clear BGP up before unicast ourselves in. Okay, here's our route refresh message. Here's our update message. As you can tell, here's our path attribute, the AS path, and it's prepending it 3 times. Why 3 times? Because we added 2 instances. We already had 1. So 2 plus 1 is 3, of course. So let's take a look at our routing table. And for the 172.16 network, right now, if we go back to our drawing, this is on the top. We're preferring router 2. Did this clear correctly? All right, here we go. Router 2, because we'll still need to apply the policy, but here you go. We got the long AS path. Let's do this quickly. Let's go to router 2. And what we're going to do is we're going to copy the route map. We're going to name it something different though. And we're going to match so on the bottom one, we want to extend the 16 network. So that is the one we want to grab. And we want to set the AS path prepend to, in this case, something longer, 64.523 and 64.523. Let's make sure our route map is correct. So in this case, we're matching the prefix list. If it matches, we are pending or prepending our own autonomous system 2 times, which will give us 3. And now what we're going to do is we're going to add it to the neighbor. Okay. Let's take a look at router 4 and see if it received anything else. Okay. So in this case, router 2 is advertising the 172.16/0 network with a AS path length of 3. Router 1 is chosen as best because the AS path is shorter, which also gives us an idea that local preference, which supersedes AS path, is also even to 1 AS path. For the 172 network, router 1 is advertising a longer AS path, making it less desirable compared to router 2, which has a shorter AS path. And if we take a look at the actual BGP reason for, when we look at the route itself, and we're going to do best path, we will notice that we have 2 available paths. Best path is the second one. And the reason for that is when we look at the first path, it says it's a longer autonomous system. So as you can see, it's 3 instances of our autonomous system that were prepended, compared to the route that was received from router 1, which is only a single one, thus making it overall the best path. Okay. Does anyone have any questions? And as shown before too, we see that this is also included in our BGP update message under the AS path attribute that it prepends it. As you can see right here, the AS path attribute is a well-known mandatory attribute as well, thus transitive. And here you can see the actual segment. Sequence and so forth, we're not going to discuss today, but just know here it says segment length, number of autonomous system 3, and it gives them to you. So while I clean up our configuration, if you have any questions, feel free to add them to the chat. And this is, again, one of those, it's a simple one, but as we discussed earlier, and Mike agreed on that, if we assign local preference, let's say on router 4, I had local preference that I preferred actually router 2 for the 172.16 network, then guess what? It's actually going to supersede what AS path was. So that's something that we will keep in mind. So let's do this. I don't want to have too much stuff sitting here, otherwise it can get confusing. So let's remove these sequences.
Always a good idea to perform some cleanup so you don't have stuff that you don't remember that you knew was around. Oh, yeah. And I mean, these BGP configurations, they can get unruly. Let's be honest, right? So, and especially with a bunch of route maps and so forth, it just gets confusing. We don't want that. So let's remove that one. Especially if you have 100 or 200 or 300 peers. Yeah. So it's simple. We're just peering with our directly connected neighbor, right? So this is a good scenario. If you're a cloud architect, you're mostly going to maybe do a couple of transit or direct connections gateways, depending on what vendor you're actually peering with or that you have within your system. So in this case, let me make sure that, okay, everybody is good. We're going to send a refresh. All right, and Mohammed says he's clear. So nobody has any questions in regards to this right now?
If you don't, I will move on to our final attribute that we're going to manipulate, and then we'll come back and we'll take any questions. All right, Chris, if you want to go ahead and share my screen. Okay, so now what we want to do is we want to influence our BGP path selection through the actual MED, or the multi-exit discriminator. So here, what we're going to do is again, we're going to do the same thing, link 1 and link 2. On link 1, for the 172.16 network, we want to set our MED to 50. And in case of a multi-exit discriminator or the metric, lower is better. And for the 172.17 network, we're going to set our MED to 100. For link number 2, which is our bottom link, for the 172.16 network, we're going to set the MED to 100. And for the 172.17 network, our MED is going to be set to, actually not 200, what am I doing? It is 50. Okay, so when it comes to the MED, it's the same thing. We're trying to influence what? We're trying to influence how traffic comes into our system, which on the flip side is going to influence how traffic is leaving the autonomous system where router 4 is at. So what we're going to do is we're going to do best practice here, and we're actually going to apply the route map with the changed metrics on routers 1 and router 2, and then we're going to actually advertise them in the outbound direction. So to do that again, we're going to add a route map. We're going to call it MED. And in this case, we're going to say route 1 to R4. And we're going to do a permit statement. Here, we're going to match. And let me do this. Do show runs. Actually, do this. Do show IP prefix. So we're going to match our IP address prefix, which is going to be, let's start off with the first one. If it matches, I want you to set, and this is the important part. I'm going to do this for a second. You'll notice there's metric, metric type, and there's MPLS label. Do not be fooled into thinking it's the metric type, because as soon as I add this, notice this. It will tell you it's ISIS, and it will tell you it's OSPF. So what we're looking to do is we're trying to use this type of metric, which now allows us to set the BGP MED. So in this case, we said 50 is what we were looking for. Then we're going to create another sequence, sequence 20. Here, we're going to match the 17 network. And we're going to set the metric to 100. And then to round it up, we're going to set an empty route map sequence. Let's make sure that it looks correct. We have route map. We're matching the correct networks. We're setting our MED to 50. So lower is better in this case. Thus, we prefer the top link than the bottom. And it looks like we're good on that. So what I'm going to do is I'm going to apply this first, and then we'll go to router 2. So let's copy this. And this is going to go towards router 4 in the outbound direction. Okay. I'm going to send a route refresh, meaning I want router 4 to be able to receive a new update message and then be able to run best path calculation on it. Okay. So let's take a look. And we already noticed the difference right here. As you can tell, for the route 172.16 that goes through router 1, we have a metric of 50. Now, the problem is, if no metric is given, the metric is 0 in iOS, unless we configure it otherwise. So that's why it's still choosing router 2 as the preferred exit. But again, that's not normally the norm. And also, I think I fat fingered here something. Right here. And let's go into sequence 20. Okay, let's clear this. Let's go to router 4, clear here. And this is the mistake I caught. We set it to 10. That's not what we wanted to do. Okay, there should be signal different, and here we go. The path through router 1 for the 172 network is set to 100, and for the 172.16, it's preferring router 1, okay, because of the lower metric. Again, we can also verify that if we look up the actual route. And this is one of those things where, again, it tells us 2 available. The best is number 1, which means this path. And if we go through the process, we know that we have no weight set. The local preference is the same. So we know we're not going to compare that. This is not a self-originated route. We see that it's an external route that we're receiving. Next, we want to look at the AS path. It is the same length. So that's a wash. Then we're going to look at the origin code, which for both routes is going to be IGP. So that's going to be a wash. And then finally, we're going to look at the multi-exit discriminator, the metric. So when I look at it, I don't see a metric yet on this because we haven't configured it yet. But notice this, it says metric 50. So it says this is the higher med. And this is the overall best path. So we need to change this quickly. So let's go here. I'm going to copy most of the route map because it's just an inverse. So let's do this. Set the metric to 100. And oh, apologize. So let's do this. Okay. Let's do the match statement. We're going to set the metric here. Let's double check that we configured it correctly. That's the route map, sequence 10. We're matching the 16 network. If it happens, we're going to add the local the med to 100. And looks like we're also correct when we're matching the 172.17 network. We're setting the metric to 50. So let's go ahead and apply this. And we're going to apply it towards router 4, the outbound direction. And we're going to do the same refresh request on, let's take a look. This should be a little bit better. Yep, okay. So the 172.16 network is right here. And it looks like we're preferring router 1 as the exit point because of the lower metric. And as a backup path, we do have router 2. Now for the 172 network, we prefer the path through router 2 because of the low administrative distance. So if we go back to running this should be correct now. You'll notice we don't have weight. Our local preference is the same. Then after local preference, we're going to look if it's self-originated. It is not. Number 1, we see that it's external. So we did not originate it. Then we're going to look at the AS path length, which is just 1, so it's equal. When it's equal, we're going to look at the origin. The origin code for both is IGP. And since it's the same, we're going to look at now a multi-exit discriminator. In this case, it's called the metric. For the route received through router 2, the metric is 100, and the one received through router 1 is 50. So the low metric wins out, making this the overall better path because this is the higher metric. And again, we can also see that in regards to what our actual BGP table says. And when we look at the show IP route BGP, you'll also notice that we're actually installing the path towards router 1 for the 172.16 network, and for the route for 172.17, we're installing it through router 2. That's going to be our preferred path. If we wanted to test this out briefly, what we can do is we can go onto router 5, and we can run similar trace routes as before. In this case, I'm just going to copy this, and we're first going to go through through 172.16. So we said we're going to prefer that towards the top link towards router 1. Let's see if that's the case. Okay. Here, we're passing to router 4. That's that connected interface here. Then we're choosing, because of the metric, to go across the link to router 1. And then finally, internally, based on the IGP metrics, we're going to cross through a directly connected link to router 3. Now, if our route maps worked in our policy, that means if we try to trace to the 172.17 network, we should be going through router 2, which indeed we do. We see that initially we go to router 4. Then what we do is we route the packet out of the interface towards router 2, which is going to be our next hop, and then finally from router 2 to router 3. So that, in a nutshell, was the multi-exit discriminator. So if you want to bring both Mike and I back on the screen, Chris, I would appreciate it. All right. For those that stuck around for this extra long BGP workshop, does anyone have any questions, any comments? Is there anything that you feel like you need clarification? I know it's been a long, long workshop, but I do hope you got some value out of it.
We hope you had some fun. We hope you learned a lot about BGP. I personally hope you join us for the AWS Advanced Networking course that's completely free coming in a week. I personally hope if you guys desire to become cloud architects that you join us in the free Cloud Architect webinar. And please go download this BGP book that we wrote for you, this ebook. Read our ebook. Heck, go out there and look at the IETF RFCs for BGP too. If you're a cloud architect, you need to know BGP. Guess what? Learn it. It's no big deal. If you're a network architect, you need to know BGP. If you're a network engineer, you need to know BGP. And let's face it, BGP is cool. I like it. So for all of you that are there, come back and watch again. Yes, Prep, definitely agree with you on that. Thank you, Michael. You wanted to say thank you for such a detailed session. You'll be rewatching this. I hope so. Chris is back there behind the scenes. I just sent him a message. He seems to be doing great. Share this with someone you know. Someone that you know that's got some goals. Send this free video to them. Let them get the free AWS working, the free BGP book. Let them join us on Thursday. Looks like I don't see questions there, which sounds good to me. So if there's no questions, I will be feeding my cat Cindy because she's been coming into the office and rubbing up against me, and that means she wants fresh shrimp, fresh turkey, or fresh salmon. I know my cat eats fairly well. But you're more than welcome, Martin. We were thrilled that you were here today. Thank you, Preb. We were so happy to see you here today.
Yeah, you guys were awesome for sticking around. We appreciate it. I know it was a little bit longer than we initially anticipated, but I wanted to give you as much detail as we could. And I will preface it this way. We barely scratched the surface on BGP. I don't want that to deter you as you learn more about the protocol, but just to let you know, there's so many things that you can do with this protocol, even within your cloud environment, that it really deserves some extra time and attention in your studies.
Yes, and it's true. And, you know, we all start somewhere. And when we start in the beginning, everything's scary. Everything's hard. It doesn't matter what it was. You know, when I was a kid and I learned how to become an emergency medical technician and a paramedic working on the ambulance, it sounded like there was so much stuff to learn. And then I learned to practice internal medicine and a nurse practitioner, and I realized, what was it? Put a mask on somebody, stuck them on a board, taped them down, and took them to the hospital. It was like no big deal. And that's the key. It feels like a lot in the beginning, and as you get better and better, you'll learn more. So, hope you guys had a great time. Look forward to seeing you later this week. We've got so many other things going on our channel, free webinars for you. Download all those free guides in the description of this video. There's lots of free things to help you in your career, and we'll see you soon. If you haven't liked the video and you enjoyed it, give it a like, subscribe, hit the bell to be notified of new things, and we will see you soon. Take care, everyone.